Hello, and welcome to this day. We will focus on power electronics today, and this day is a joint venture between KTH, RISE, and Smartare Electronic Systems. And as you have seen in the program, we have an agenda with very exciting topics today. And we will start with an international perspective, and we also have a visitor here that is from Katech, Dr. John, and then we will move on to specific topics from different companies, and during the day you will also have the possibility to have impact on our agenda for electronic sector. And we will also be able to listen to specific presentations of recently done studies. So a warm welcome to you all, and I will leave this to you.
Thank you. So welcome to KTH. We are in Sal A. This is one of our lecture rooms. In case of emergency, there are exits on both sides of the front here. Restrooms, you have to walk all the way back out and take a right from where you came. It says water closet or WC on the wall to find them. In case there is a fire and we have to evacuate the building, continue in that direction, and there's like a bull court with gravel, and this is where we gather. So thank you for coming.
Thank you. So those of you who don't know me, I'm Claes Brinkfeldt. I'm from RISE, and I just want to say I'm very happy that we can arrange this Power Electronics Day yet another year, and I hope we have a very productive day.
Thank you, and I never told you who I am. I am Anna Wibom, and I am the program manager of the Smartare Electronic System. And Bellman, Carl Mikael Settling from KTH. Well, our first topic will be regarding the CHIPS Act, and I will leave the word to you, Mikael. Thank you.
Good morning, everyone. Fantastic to see so many people so early interested in power electronics. There is hope for Sweden and for Europe. Yeah, my name is Mikael Östling. I have my office 50 meters from here, so I'm very used to this environment, but I'm not used to so many people looking into power electronics, so it's fantastic. So, and I want to thank Smartare Elektroniksystem for initiating such a day with just power. That's fantastic. Thank you. So in my presentation, I'm going to touch upon the European CHIPS Act and the CHIPS joint undertaking, but I will do that together with Adela and Björn. And we will have different parts here. So if there is a short question, I might be able to answer it, but otherwise we leave the deep questions to afterwards. So this is quite astonishing that Europe finally got together and said, Europe needs a CHIPS Act. We need to bring back the chips and chip manufacturing to Europe. The Commission President, Ursula von der Leyen, had a quite interesting speech in 2021. And she told about the objectives of Europe. And that is, of course, let's see if this one works now. I should point to the computer, I was told, and you can see that. Strengthen the research and technology leadership. And one thing that has been very strong here is basically that we had that initially in the 80s and 90s, but like everyone else, this moved further to Asia, and now we realize we have to take control. So the CHIPS Act is engineered to do that. We want to have design, manufacturing, packaging of advanced chips, And here is one disclaimer. I think when we speak about CHIPS Act in general, there is not so much talk about the power electronics. So our mission here is to talk about power electronics and get that back into the CHIPS Act. Because everyone thinks about these mega fabs like we have seen in Taiwan and so on. And that's not for the real power. This is a project lasting until 2030, basically, and then we should have been able to bring back a lot of technology and manufacturing here to Europe. How does it look when we look today? We have, this is what we have in the value chain in Europe. There is not too much of IP and electronic design, but it's much more on the raw material, silicon wafers, silicon carbide wafers, of course, gallium nitride wafers, and so on. And Europe is pretty big in manufacturing equipment. I think you all have heard about ASML and the state-of-the-art lithography for the tiny, tiny 2-nanometer technology. This is a war going on in the world, a trade war where Europe is blocking deliverance to China. US is doing the same. China is probably doing the same to us. So there's a sort of trade war going on. And hopefully we can mediate that by having more manufacturing also in Europe. R&D is basically pretty strong in Europe, but chip design, manufacturing, assembly and packaging needs to be sort of scaled up. So the EU strength is the green bubbles here, and we need to shape up on the other ones. Some of the goals that has been said is that we would like to bring back, so we have manufacturing consisting of 20% of the world market in Europe. So CHIPS Act has been negotiated, and we can say that the numbers are basically set. There is a 43 billion euro funding that is agreed on. It's both public and private funding, mostly private. To realize the 20%, me and Adela was in a workshop in Amsterdam just before, in November, I think, last year. The CEO of NXP mentioned that to bring that goal, to realize that goal, we need about 500 billion euros. And of course, that's not governmental or state money, it's the private investments that needs to be done. So it's a huge thing that must happen if we are bringing back 20% of the manufacturing and so on to Europe. So there is plenty of opportunities here if we play it correctly. One thing that is also mentioned in the Ursula von der Leyen speech is that we have to train talents. Unfortunately, I haven't heard so much about that discussion in the meetings I have been to within the EU, different EU meetings I've been to. So I think this is the most urgent thing, and we have come to the right place. For example, KTH. We have quite a lot of semiconductor education, but we have a good situation in the whole of Sweden. We have in Lund University, in Chalmers, in Uppsala University, somewhat in Linköping, on the real semiconductors. So we just need to expand that. We have the infrastructure for it. We need to expand it greatly. So the Horizon program, Horizon Europe program, is divided in 3 pillars. So apparently EU wants to have these 3 pillars to better explain what's going on. Pillar 1, which is mostly for the university people, is basically excellent science. And then we have Pillar 2, which is the industrial competitiveness, and pillar 3 is innovation and all that. That's the general structure of the Horizon program. So the CHIPS Act, surprise, 3 pillars. We have the first pillar is Chips for Europe initiative, and then pillar 2 is security of supply, and pillar 3 is monitoring and crisis response. So I will mostly focus on the pillar 1, and Adela will also talk about pillar 1, and Björn will talk about pillar 2, I think. And 3. Pillar 1 is, of course, about the initiative on the building the infrastructure, and also a very large focus is on getting smart startups in this field. So I think that is where we can contribute quite a lot here in Sweden. And then there is this slogan, from the lab to the fab, which is, of course, logical. We need to take the research activities in the lab and bring it to something commercial success. We have lots of exciting track records on doing that. We need to do it even more. We need to do it even with larger expansion of the startups. Today we basically have a very functioning startup, and then we sell it off either to a US or European vendor. I think we can really expand on this and get manufacturing back to Europe, to Sweden, not just to Europe. So here is the scenario that has been launched by the Commission, and the thought is that we should use different labs and fabs in the different member states to get the whole picture. Not everything in one place, but maybe work together here. Let's see what I have. I can go back to this one and discuss a little bit more. The thing is that we have the major 3 RTOs, research and technology big institutes. The 3 big institutes we are speaking about is CEA Leti in Grenoble, we have IMEC in Leuven, Belgium, and we have Fraunhofer institutes a little bit spread out. And they are like, really big infrastructures. They have invested so much. The Commission thinks it's also something very important. The whole system is rigged to continue to support these gigantic research institutes. Of course, we have nothing of that size in Sweden or Scandinavia. We have these 3, so they will be number 1 in priority. That's my interpretation. Let's see what Adela and Björn thinks. But what has not been too much discussed is the other levels, where we have the fantastic other research institutes, and particularly the university semiconductor facilities. There's a lot of those around Europe. And also here in Sweden, we have, of course, fantastic resources for bringing things not on the commercial scale directly, but to pave the way for doing that. So one organization that we have been very much involved with is the Sinano Institute, with its site in Grenoble. And you see the picture in the middle there is the Minatech facility, where we have up here is the Leti facility, and here is a more university and institute activities. That's one of the leading places in Sweden, in Europe. And we have 25 member organizations. You see them listed there. I guess these slides will be also available afterwards, will they? So you can check for that. Of course, CHIPS Act is heavily discussed within this kind of research institute. And I was just there last week, and I'm the chair of the General Assembly for this organization now, so I have some insight there. So they will, of course, promote the thoughts that we have here in the university world and the institute world, that we are not just focusing on the super big institutes. ICOS is a project that is coordinated by Sinano Institute. It is a clear focus on international cooperation on semiconductors. And international means we are focusing on how can we relate to the Japanese, to Canada, Taiwan, and South Korea, of course. So there is a big, big focus on also being international, not just European. We need to collaborate. And just to mention, there is a US CHIPS Act also launched. They are 1 year ahead of us here in Europe, and they are also focusing very much on education. The big universities in the US are really getting together. Of course, they have to compete a little bit. They write proposals for this and that. So I'm not sure how much they have really launched in that, but they are already looking for the money. And some of the Swedish companies are also looking for the money in the US. So we are a step behind. But ICOS is a very interesting project. I'm involved to look at the road mapping, and I will come back to present that after the break. There's another initiative called Ascent Plus, which is coordinated by the Tyndall Institute in Cork, Ireland. And here it's also like some sort of Swedish MIFAB, where some of the labs are offering processing services. If you're a researcher and you don't have your own lab and so on, you can basically use the Ascent Plus lab. So I put it here, and you can Google it later on. But our crown jewel here in Sweden is, of course, the MIFAB, whatever you want to call it. It is the 4 major university labs for doing micro and nano fabrication coming together, and you see some of the fantastic numbers. We have like 700 instruments and 800 active users per year, many companies, and so on. So we have a distributed infrastructure. Some of that is, of course, the same equipment in all the 4 labs because it's bread and butter, but we have coordinated the whole thing, so there is a sort of complementary setup. So not everyone has all the fantastic equipment, but we can use each other. It's a common system. So this is the crown jewel we have in Sweden. And the capacity is, of course, we can double the capacity if we have interest. So it's just a funding matter. But this has generated so many good companies over the years. We have, in this building, we have the Electrum lab, which is one part of the MIFAB. So some of the reflections before I end. We have this very strong infrastructure, even if we are not so much publicizing what we are doing. But we have it, and we have it in the university system. And RISE, of course, is involved. We have a very good track record with many good micro and nano companies started from here in Kista, in Chalmers, Lund, and Uppsala. What we have is also a quite unique education, because we have Master of Science classes for semiconductor technology, where people are actually hands-on in the lab, hands-on in the measurement lab, at the computer to do simulations and so on. So it's a full-fledged educational system. Of course, we can expand that. The problem is, how do we find interested students? How do we get the attraction to this area? So I've been talking about the narrative, why we should really change the wording when we speak about semiconductors. No one under 20 today is interested in semiconductors. It's like before the invention of the transistor. Are they real? Do they exist? But they can do so much for the sustainability in the world. I come back to that. So we need also to synchronize our efforts in Sweden. Normally we just compete. We have a proposal from KTH, one from Chalmers, and we head on bang it like that. That is not sustainable. We need to have a complete view of this, of the educational system and the resources we have in the clean rooms and so on. So let's have that as a motto when we take the next step. So I think that is basically my reflections here, and then Adela will take the joint undertaking further and the Vinnova process. Thank you.
Thank you, Michael. Adela, you will continue, and we will dig deeper down in the CHIPS joint undertaking.
Yes.
And then Björn will continue. And Adela, she is from Vinnova, and Björn from Tillväxtverket.
Exactly. Thank you very much, Anna. Okay. Thank you for the opportunity to be here today. It's very good to be able to talk to you about what's going on around us in Europe and the discussions that we have been having with other countries and with the European Commission. Thank you, Mikko, for a very good introduction on the CHIPS Act and the objectives of that. So I'm Adela Saavedra Granholm. I work at Vinnova in the Department for Industrial Development. I'm the lead delegate at the public authority boards of the program. That's a partnership program within Horizon Europe, called Key Digital Technologies. Vi har rundgång, antar jag? Nej. It's the program that's going to be changed to be called CHIPS Joint Undertaking, and there will be other budgets and other activities included there. See? And I have with me today other colleagues from Vinnova. We have Lars Gustafsson. We have working in KDT, is the program, as Sverker Brundin, also delegate, and Staffan Nilsson that works with Smartare Elektroniksystem. So there are more people around if you want to ask questions in the coffee break, right? So as I was saying, the CHIPS joint undertaking will be the continuation of Key Digital Technologies. That is the partnership we are working on right now. And what's going to happen then? What we see today is that KDT has a lot of the activities you see on the right there, research and innovation projects. We have calls every year, and it's about research innovation actions, coordinated specific actions. And we don't have other activities, let's say. We just are focused on the calls, and there are conferences like matchmaking sometimes, but that's the focus of the program today. But what's going to happen based on the CHIPS Act implementation? So that program will have, let's see if I can get that. Yes? So that part is KDT today. What's going to be added is other research innovation activities. That's going to be part of the work program for the CHIPS joint undertaking. That's done yearly. That's going to continue to be as it is in KDT. And the new part, let's see, yes, that's on my left side. And it's about the large investments that will be done in Europe along the program year. I want to remind us that this is to 2027. We have been discussing with Commission because we need commitment for beyond 2027 because it's not going to be enough until 2027. And we will talk about that a bit. So the CHIPS for Europe initiative, that's the expansion part, the large investments part that we don't have at KDT today. That's going to be the new part in CHIPS joint undertaking. And that's including like Mika was pointing out, what we call pilot lines. That's not for production, that's for research and innovation. So that sometimes people hear pilot lines, they think about factories, but that's pretty much like we have here MIFAB. And design platforms, so we are weak, as Mika has also pointed out, in the design of the ships and integrated components. So this will be an European design platform that we will see cloud-based. And competence centers, that's not the same thing as we found in Sweden by Vinnova, SSF. We found centers of excellence. That's not the same thing, but we will look into that. And skills, there will be calls about skills. And quantum, pilot lines, research innovation projects, it can be all different kind of activities. And you see the budgets down there. So as I was saying, the investments are on this side, and that's the budget. So about if we start to look into the different initiatives within the Ships for Europe initiative, you see the competence centers, that's part of the Ships Act. A network of competence centers will be established around the Union. And is really to give the support to the first case, SMEs around Europe in this area, but it's going to be including the academic and the large companies as well, but it's a lot of focus on the SMEs. Services for the SMEs and education to address the lack of skills. We don't have enough resources in Europe for the need that we see. Some of the characteristics of those competence centers, so each member state will have the possibility to apply for support for at least one competence center. So that's one of the statements. So it needs to be a co-investment. So if the country needs to fund, and then the Commission is going to match the funding. Supporting industry and public services, there is also this area. Focus on education, you see there are semiconductor skills, and to coordinate, to support the SME and other users, the access to the, call it pilot lines, and then to the design platform is kind of in the center of this network to connect between the actions. The other action is the design platform. And you see, I'm not going to read everything because you will get this material as well afterwards, but it's really to mount a cloud-based platform to reduce the barrier for those small companies, for instance, or academics, to have access to this kind of facility. Will be a framework that's already that will be in place to make it easier to use and not be afraid of that your design is there and it's not secure, somebody else can take or whatever. So there is a lot of thinking about that. And there is a group based on companies and some academic partners, but we don't see that there is a Swedish company there working in the, to form how this platform is going to be implemented. That you see some highlights of what I was trying to say. So it's a complete ecosystem, starting from designers. So you see activities in training, support, design services, all the way until you get the PDKs, and then you go to the fabs and the pilot lines. And the competence centers will be a way to ease the access, to coordinate and to help the SMEs to find out how am I able to use those services for the design platform and for the pilot lines. And I was thinking about the pilot lines when Mika was talking about that. It's Excel was the previous partnership program. And in that program, there was a lot of investments in the call it pilot lines as well. So it's about upgrading the pilot line that exists in Europe. MIFAB is an example, that could be the case. And making new pilot lines. So it's a mixture of upgrading, expanding, and making new ones. And in this, this slide is showing the information that we received in the last public authority board meeting. This can change. That's why we are very clear about that. So this information, maybe the distribution of the budget's not going to be like this. So next week we have again public authority boards. Maybe we will hear some new distribution, but that's the status right now, so that you know. From my right here, let's see if I can go into the details here. So you have the ship's joint undertaking activities as we have been having at KDT. So it will be open calls every year at least. We will have in 2 stages with the project outlines, full project proposals, takes the whole year, the whole process. And the base of those calls will still be the research, strategic research innovation agenda that's promoted every year and reviewed every year, focus on electronic components and systems. That's the base of the call, and we say that's the bottom-up part of the call. It's, we are expecting, and that's a dialogue we have with the Commission, that the focus topics, that is, there are topics that we think they are important. Sometimes the Commission driving them, sometimes it's the industry, and we are trying to come to a consensus what should be done right now, what needs focus. And those are the, call it, focus topics that are discussed in the governing board of today KDT and UB Ship's Joint Undertaking. One important thing to think about is the founding model. So if we put 100 euros, the Commission is going to put 100. If we put 0, they are not putting anything. So in the beginning of KDT, the first 2 years now, we are going to the third year, third call. The Commission has been giving grants, conceding grants, to organizations when the nations couldn't do that. There are some requirements. The project is there and not all the participant states are able. They are founding. In our case, that happened. I have a summary of KDT projects at the end, so we can look into that. But NETS is not supposed to continue. So if the member states don't have the budget, the Commission is not willing to continue supporting those organizations. So it's very important for us to have that in mind. And all the funding is coming from the budget for Horizon Europe, okay, from this right part, as it is in KDT. If you look now, the left part, you see the distribution for, and it's not really any surprise that the pilot lines takes most of the budget. It's very expensive to buy and to build and to expand. Whatever you're going to do is not cheap. There is a lot of need for investments. So that's the larger part of the budget. About the competence centers, you see, it's 200 million euros allocated. And what we receive from the Commission is that will be 1 million per country. That wasn't the first information we got, but that's the latest one. So besides, if a large country would like to have about 4 or 3 competence centers, they are getting the same budget as another country that's just going to establish 1 center. That's the information we have right now. And again, for all those investments, we need to match. It's going to be 1-to-1. So if the Commission is investing, we are investing. There is another budget, that's they call it the Ships Fund. That's about 300 million, and it's going to be distributed through the European Innovation Council. That's part of Pillar 3 in Horizon Europe. It's not part of the Ship's Joint Undertaking. So that's a separate process to reach the fund. This is the plan for the first calls. So you see, this is what's happening right now. It can be that next week the time schedule will be a bit shifted. But interesting to see is the call in digital programs already open for the skills. So it opens now in May. It's going to finish to close in September. So that's one you can start looking into. And we are expecting the first calls for research innovation projects in Ship's Joint Undertaking to open in the beginning of next year. So I have some comments there, so I think is good for you to know about. That all this is like preliminary, and for the competence centers, the member states needs to nominate. So that's going to be the process only for the competence centers, not for the other activities. So now we would like you to pay attention to the numbers. So we have an issue with the budget from Vinnova side. Vinnova has today the responsibility to represent Sweden in those in the partnership, and for that we have to allocate budget. We have been allocating 50 million crowns per year for KDT, and we see that that's not enough, and it's not going to be enough for the ship's joint undertaking. So we need to have an increase of the budget. And what we hear from our department, our minister, is that the industry needs to step up and say that this is important. Otherwise, we are not expecting to get any, because if the academic Tillväxtverket or Vinnova is saying that's very important, that's good, that's fine. But the industry that needs skilled engineers and technicians, they need to have the possibility to say what they think. So if the industry is not saying anything, so probably we will not get larger budget. That's the situation right now. We are doing what we can, and I think in that way we are working together, because in different places we will need to have more budgets. In the organizations like us, the public authorities, but not only here. And what you see there in the second line, the white line, is what Vinnova has put it in our proposal to our minister, what we see as a need going forward. And you can think maybe it's too little money, maybe it's too much money, and then let's see what is happening with KDT. We have been able to fund 11 projects so far in the first 2 calls. There were more projects. Last call we couldn't fund 2 projects, so there are 4 organizations in Sweden that couldn't get funding from Vinnova, and they got from the Commission. But we are not expecting that to continue. Okay, so that's what I had. Thank you.
Well, we have some technical issues, but soon we will be on the run again. There we are.
Okay, excuse me for the technical problems, but now we're up and running. The European Chips Act consists of 3 pillars, as said before by Adela. The pillar 2 and 3 she didn't mention, so I'm going to talk rather briefly about them. The main thing of the pillar 2 is the first-of-a-kind production. The goal is, as we have already heard, increased production in the EU. And state support for the investment could be up to 100% of the investment cost. But it is, as mentioned before, it's 50% from the EU and 50% from the member state where the investment is done. But in order to be able to receive this much financial support, you must have the status of being a first of a kind. That means first of a kind within the EU. So that is production that is not for the moment present within the EU, but it could be present somewhere else in the world. That is one thing that was changed in the negotiations before, because first it was said first of a kind on a global level. But that is not a very good way of increasing European production. It could be either an IPF, an integrated production facility, or an open EU foundry, so that the different kinds of production facilities. But what we see is that we think that parts of MyFab could be first of a kind and could be pilot lines and could have the status as the first of a kind. The first of a kind is production of chips. It could be front-end as well as back-end production. And also, that was during the negotiations put into the CHIPS Act, production of equipment. Since we are strong in Europe and we want to continue to be strong in that area. So of course, first of a kind could be also production of equipment. It was proposed to have design in here, but it was taken out because it's pure production, even though design is closely linked to production, of course. The facility must contribute with innovation for production processes or to the final product. So it must be innovative, of course, but first of a kind by itself is part of it, is sort of innovative. And there must not be a similar facility within the EU, of course. But this is rather important because you apply for being a first of a kind to get hold of the investment. So you must be rather fast. Because if you wait too long, someone else might apply for and get well, you are the first of a kind, but they're not starting the investments yet. So you must be, we need to have rather high speed here so that no one else is taking first of a kind where we could be in Sweden a first of a kind. It could be a completely new built facility, or it could be upgraded, an existing facility that is upgraded partly or as a whole. So it's very important that it must not be a new building. It could be upgrading within existing facilities. The pillar 3 came as a result of the crisis where the problems to have semiconductors delivered. The aim is to realize that there is a crisis upcoming and realize it early enough to be able to do some actions to prevent the crisis to get in full effect throughout Europe. The Commission will monitor the semiconductor industry and what is called critical sectors. And critical sectors are health, it's security, it's defense, and that sort. Some of you might have heard that it has been talks about the transport sector, including manufacturing of cars and trucks and so on, but that is taken out. It's not a critical sector for the people in the EU to survive during a crisis. We need cars and we need to transport and so on, but it's of vast importance for European economy, but not for us to survive on the short line. So that's why it's not a critical sector. If there is a crisis upcoming, the Commission will propose to the Council, and the Council will vote and say, yes, there is a crisis now. And the first decision will be that the crisis will last for 12 months, and then it could be prolonged by 6 months each time. But there is also a European Semiconductor Board, which consists of people from the member states active in this sector, and the Semiconductor Board will give its view to the Commission before they are proposing anything to the Council. And when the crisis is present, the Commission get a possibility to use different instruments. For example, the first time when they are monitoring the sector, they ask for information from our companies, but it's not mandatory to answer. But if there is a crisis, the Commission goes out and asks companies, and they must have they must respond, and there will be a fine if they are not responding as they should. Also, the Commission can prioritize those facilities as having received the first of a kind. The Commission can go in and point out, you must not serve those customers, you must serve these customers instead, and so on. So it's the Commission overrides the decisions of the actual facility. But the Commission can do a common purchase for the whole EU on the world market, and of course that's mainly for the smaller companies that are not strong enough in the negotiations with the big ones in the world. And the EU Commission is considered to be a stronger part to be able to do this purchase. So that's the pillar 3. Now, what will be the roles of the public authorities? We have an assignment from the government to propose how the CHIPS Act should be implemented in Sweden. We are working with that for the moment, and it's mainly it's me and it's my colleague Julius who's sitting up here in front. We are doing that for the moment. The government has asked us to propose this by the last day of October, but we have said that's too late. So we are writing our proposal for the moment, and we are going to hand it over to the government in June, because it's important that it can be actions within the budget process for the next year. And that October is too late because the budget problem is proposed by September. We will point out which authorities should have what role, and there is no surprise. We will point out that Vinnova should continue to work with the Pillar 1. Of course, everything else would be stupid. So and the government will go in that direction. They will not point out someone else, of course. So you don't have to be afraid of that. But who is going to take care of the Pillar 2, the investments? And who is going to take care of the Pillar 3, the monitoring on the national level? It might be we at Tillväxtverket will get that role, but it's not yet decided. So we don't know that yet. It also could be that we are responsible for the state aid and all the governmental support for investments in IPF, in first of a kind, IPF, OEF. We do have that role today for investments in certain areas of Sweden, and that's mainly the inland of the northern part of Sweden, like in Östersund and Gällivare, and in the ski resorts and so on. All those areas, they can get investment support. But we don't have investment support in other parts of the country. But one thing that might happen is that we do get that role since we are working in that area already. Do we get more money? We don't know. Is it impossible to get more money? Not really, is what people say to me. I've been talking to some of my bosses who are more experienced in how you negotiate with and how you try to raise money in this. It is not unlikely that we do get some more money. But we do have a problem, because the Swedish standpoint is that governmental support for investments is not good. It's not good when the government interferes in the public market. So we do have a problem here, because we need to have our government to little bit change their standpoint in this particular area. So if you meet any politicians, talk to them and explain to them. But one thing that we need to do is that we need to gather the information of what have been the outcome of the research we have had so far. Because if we in Europe should increase our production until 2030, which is not very long time, we need to invest in what we have already done in research. So we must really say to them that this is what we have gathered so far, and now we research for getting the next step. But we do need to do investments now. But we'll talk more about that later. And that was it. Thank you.
Thank you very much. A big applaud for all three of them. And now I wonder, do we have any short questions? No, it was crystal clear. Well, only long questions. But I would suggest that we take the long questions in the break. But now we have Dr. John from Katek in South Korea. A warm welcome to you, and you will give us a speech regarding reliability and functional safety issues in semiconductors for automotive applications. Please, the floor is yours.
I'm glad to presentation at Power Electronics Forum 2023. My name is Dr. Kyubong-yeon, and I work at the Korea Automotive Technology Institute.
Like this.
Oh, yeah. Better than? Okay? Yeah. Let's start. I'm glad to presentation presented at the Power Electronics Forum 2023. My name is Dr. Kyubong-yeon, and I work at the Korea Automotive Technology Institute. Katek was established through investment from Korea government, 1,000 auto part company and Hyundai Motor Company and other company. My presentation will focus on the reliability and functional safety issue related to silicon carbide semiconductor for automotive applications. Content consists of motivation, overview of silicon carbide solution for automotive, R&D goal, and content with the reliability issue, commercialization and benefit, summary. xEVs are being developed with high efficiency and high voltage electronics systems. And as a result, there is a need to transition from silicon IGBT technology to silicon carbide technology. This picture shows the semiconductor power device market for xEV, and it is predicted that the proportion of silicon carbide will increase rapidly. The characteristics of silicon carbide power semiconductors include stable performance with a wide energy band gap, high current control with low loss and high frequency, and high reliability with low channel resistance and small device thickness. When compared to silicon power semiconductor, this picture shows that silicon carbide has both high frequency and high power characteristics. Compared to silicon IGBT, silicon carbide has the advantage of reducing the size of device chip, as can be seen in comparison with other type of device. This slide provides an overview of project with focus on the PTC heater system and the consortium organization. The PTC heater system is high efficiency electric vehicle heating system that utilizes the positive temperature coefficient effect. This project is being supervised by the Korean government, Ministry of Trade, Industry and Energy. Caltech serves as the general manager, while RISE is responsible for developing the silicon carbide component. Labotech is in charge of the PTC heater controller, and URI is responsible for the PTC heater module. The final product of the project is expected to supplied to automotive companies, such as Hyundai Motor Company, through Hano system. The slides show the development of PTC heater module controller with silicon carbide. A replacement from IGBT to silicon carbide is required for this development. It is expected that one of silicon carbide can corresponding to 3 silicon IGBT. The PTC controller will develop with both functional safety technology and virtual qualification technology applied. Virtual qualification technology is reliability simulation technology that takes into account the influence of temperature and vibration in harsh automotive conditions. This slide shows the related reliability and functional safety issue related to automotive powertrain applications. The picture indicated the Automotive Electronic Council qualification standard. In automotive power application, AC grade 1 and 0 are required to operate at temperature ranging from minus 40 degree to 150 degree. In automotive safety application, AC grade 1 is required to operation temperature ranging from minus 40 degree to 125 degree. An important aspect of HQ assessment test is that must satisfy the electromagnetic discharge requirement issue. 3 out of 5 items in the HQ test related to ESD, indicating the importance of addressing reliability issue. To address the harsh environment in vehicle, fault in automotive systems are caused by thermal vibration and electromagnetic interference problem. Test method standard exist for individual problems, such as high accelerated life cycle tests. However, these problems are not independent, and therefore, the standard test method that used integrated fault injection is required. In recent years, there has been increased demand for highly functional safety semiconductor in vehicles, such as system on chip with a high autonomous safety integrity level in the area of autonomous driving controllers. The reliability test of semiconductor is crucial for ensuring safety in autonomous vehicle unit that are at risk of fault. The image depicts the 4 AC level, named AC level D, C, B, and A. For AC level D, probability of violating the safety goal should be 1 fault in 100 billion hours. The single point fault metric standard should be less than 90% for AC level D, and latent fault metric should be less than 90% for AC D. In harsh operating condition for xEVs, fault can be caused by combined of thermal vibration and electromagnetic influence. This requires an increased focus on reliability requirement. To ensure reliability in automotive applications, we have a plan to conduct development, reliability tests, and actual vehicle tests. Uri Industry, which is involved in the project, already supplied IGBT-based PTC heater system to Tesla in their business. Once the project development is complete, in cooperation with RISE, we expected to increase our global market share. We also look forward to expanding into various application fields through global joint research. In electronic vehicle, various voltage levels are used for module and component, which is why more power semiconductors are expected to be required when designing power semiconductor for electric vehicle. Safety margin up to 120 volts needed to be taken into consideration. xEVs are being developed with high efficiency and high voltage electronics systems. It's required to device transition from silicon IGBT to silicon carbide technology. The automotive fault is caused by being together with thermal influence, vibration influence, and electromagnetic interference. The automotive reliability requirement is increased. In order to secure reliability for automotive, we plan to conduct development, reliability tests, and actual vehicle tests. Thank you for your attention.
Thank you. I have a question. Is there any issue on the packaging field in the automotive application in Korea?
Yeah. Already answered. In Korea, there are several issues related to semiconductor packaging for automotive purpose. The automotive industry in Korea requires various specialized packaging depending on specific application of each automotive component company. Additionally, there are concerns about reliability and functional safety issues, such as temperature, vibration, electromagnetic compatibility, and diagnostic capability, functional safety, concerns related to automotive packaging.
Okay.
Thank you.
Thank you. Now we have a break. Thank you. And now we are going forward in our program, and we will listen to Mikael Östling again. And as he was before, he's still from KTH. And he will tell us about the WBG discussions in International Roadmap for Devices and Systems. And Claes, you wanted to comment something also? Or we take it later? Okay. After lunch. Please, Mikael.
Screen, Bellman. Magic. Power electronics behind. Hi again. Good to see the energy that you have. I love these discussions, and it's difficult to get you seated again. In this talk, I will tell you about the work that is going on to roadmap the power electronics. First, I will give you some narrative, how we can argue for the importance here. We have some societal challenges that you're well aware of. We have to conserve energy. We have to produce energy in a fossil-free way. Most of that energy, the electric energy passes through power devices. Okay, so we can do something about it, even though we cannot maybe control this guy too much. That's out of the electronic engineer's control, but we can do things for it. So here is the situation we have today, the world consumption of electric energy. And we see that around 26,000 terawatt hours are consumed, and by maybe 2045, who knows, earlier, we have doubled that. And that tells us that, okay, we need to be cautious in the way we are spending the energy, because here is the sad story. Here is how all that electric energy is produced. So 63% of it is basically fossil-based. That's bad, super bad. Here is the biggest spenders, China, US, India, Russia. And we know that those countries are really into this fossil-based production. So that's also very bad. Luckily, Sweden is not on this scale. How can we do something about that? The efficiency. Well, we can, of course, argue that the energy mix is improved, and that is done all the time. But at the same time, we can make a change by studying and producing new types of semiconductors. So we can build efficiency in the production path, and in the distribution path, and in the way that we consume this energy. There's a lot of power device stations to control all that, and we can make it so much more efficient if we are using the new type of semiconductors. The wide bandgap semiconductors has been a very established technology today. It's still not at all as big as for the silicon based power electronics, but it's coming up, and with the electrification of the society, this is really shooting up. Just an example here, and we know that mostly we have the silicon carbide, which is the most mature material of these wide bandgap materials. Gallium nitride is coming very strong, and there is a lot of other materials also, ultra wideband gap materials that are of interest, especially for researchers. Lots of papers to be written there. But take this example, if we improve the efficiency 1%, then those numbers I showed in the previous slides would save us up to 75 typical sized coal-powered power stations. Just by increasing 1%, we can do so much more than 1%. But and that's what the whole thing is about. I think that is a general argumentation that we can use. So wide bandgap materials are defined as within the more than more regime. This is an old picture that you might have seen before. We have the scaling on this axis, that's the more, the super small chips. More than more is basically other functionalities. We have naturally the high voltage and power. That's where we belong with the wide band gaps. So there is an ongoing IEEE, International Roadmap for Devices and Semiconductors, devices and systems, that are divided into 4 sectors: smart sensors, smart energy, energy harvesting, and flexible electronics. I have now been also responsible for leading part of the work in this smart energy sector. And I want to just mention a few things that is ongoing. What is the focus of that road mapping? Here's the team. I just took it over, so I haven't met all the guys. I know many of them, and some of them have also changed affiliation since this was established. Some of the obvious focus areas: gallium nitride devices and substrates, silicon carbide devices and substrate, and of course, looking way into the future, what can be also of interest are the new materials that are so much more immature, so they will take lots of time from now until they are in massive use. Aluminum nitride, gallium oxide, diamond are the common ones. I will not mention them in this talk. But the roadmap is basically considering these kind of things. Lots of text, of course, but name of the game is high efficiency for these new technologies. But it's also not just devices, it's also the wafer material, because the wafer material is setting the performance of the devices still. Silicon is a little bit more simple material to get into shape, but all these compound materials always have inherent defects. It's a fantastic progress in minimizing these defects, but still it's of major importance. And we need to also still not forget the silicon, but since this is more on the wide bandgap thing, I will not mention too much about that, but never forget silicon. Silicon is the dominant power device material still. Power management for both high voltage and for low voltage. And of course, that was mentioned in the last talk here, the packaging. The packaging will become super important in the future. To handle these massive megawatt powers that we are expecting from these semiconductors needs to have intelligent packaging, new materials, new issues with the temperature coefficients that is not as simple as for the silicon technology. So I foresee that there's a lot of those questions coming up. The white paper, I have also indicated an address in one of the slides to the white paper, has defined these kind of challenges in the short term until 2025. You see the gallium nitride part here is basically substrates, devices with the common things, minimize leakage, increase reliability, and so on. New gate structures to control these gallium nitride devices, and how you can also be able to do reliable and low ohmic contacts. Modules comes into play naturally. And about the same thing with the silicon carbide. There's a lot of device exploration, new type of devices that are more efficient. We see more devices that comes into the form that we have in silicon. For example, IGBTs have been on the research scale quite interesting results reported in conferences. Still, it's not a commercial technology yet. You have to combine the MOSFET technology with the bipolar technology, and that's a challenge in itself when it comes to silicon carbide materials. But you see, lots of focus is on the substrates. Interesting here in this building is that we have a new company very much focusing on defect-free silicon carbide 6-inch, 8-inch substrate, G-sub. And that is really important for the future. The cost for silicon carbide substrates is still a major issue. We will see how it comes along. Many of the gallium nitride devices are actually built on silicon carbide substrates. So gallium nitride on silicon carbide doesn't have a cost advantage. You need the silicon carbide substrate for gallium nitride devices to get the maximum quality of the devices, especially for RF power, because there you are dependent on linearity of the RF part of the device operation. So we will work further on this roadmap, maybe also define a couple of new figure of merits, and looking to the whole benefit of the cost cycle analysis. What does it cost to produce these devices versus what benefit do we get from them? I think Bellman is very concerned with the time, so I will rush through the slides. But there's a lot of investment in silicon carbide in Europe. I have just mentioned a few things, and I'm sure you know a couple of others. Bosch, Infineon, ST Microelectronics, and Wolfspeed are really expanding here. I'm not sure if this was the table we saw before, but you can see that the prediction of the silicon carbide power device market is fantastic. This is from Joel. No, this is from the TrendForce. Joel has a similar prediction. $5 billion in a few years. And you cannot read this text, I know that, but you can see the slides later on. Here is what's going on. There is a battle, basically, the merger and acquisition of different companies. And we have seen these fantastic happenings here in Kista. Several companies in the silicon carbide area has been acquired by American companies. So this is going on both in US, but also in Europe, Japan, Korea, and China. So it's a really fluent market here. ST Microelectronics have announced that they will they are not just pleased with the Norstel factory that they bought. They will also double that with a setup in Sicily, in Catania. Bosch expanding like crazy, also focusing on several technologies, not just, they have silicon carbide, and gallium nitride. Infineon is maybe the strongest investor right now, with lots of new acquisitions, and they are also really targeting Villach in Austria as the power base for wide band gap. You can have a look at that later on, but here is just a picture I found yesterday showing the number of investments that goes on. So basically, there is a lot of push in this field, and I feel that we have to act now in Sweden to not be left too much alone. Wolfspeed had this fantastic view of their new setup in Saarland in the south of Germany. And this will be one of the most powerful fabrication facilities. So with that, I think I almost managed to be in time. And maybe we have 1 minute for comments.
Absolutely. Do you have any questions, remarks?
Krista?
Yes, we have one question. If you say it, I repeat.
This $800 figure you mentioned, was that the actual or a target?
Okay, the $800 figure that you mentioned, was that a target or is it?
I think, let me just give you an example. When we started the company called Transic, we went to the automotive industry and said, this is something for you. We had a very powerful transistor. Well, it's interesting if you can provide it with a figure of merit like 10 cents per ampere. So I think you can get $800 wafers, but it depends very much on what are the specifications of that. But you cannot get $800 for an 8-inch wafer today. So it is you need that number to be on the market.
More questions? No. Thank you very much.
Thank you.
A big applause. And now we will have the opportunity to listen to Carl-Mikael Zetterling, and he has been appointed Teacher of the Year at KTH last year, and also IEEE Fellow. And I think that is worth an applaud.
Thank you, Anna.
Thank you.
Can you hear me? Yes. So now it's back to the school bench with a little wide bandgap semiconductor device primer. So my name is Carl-Mikael Zetterling, and I'm the head of the division of electronics and embedded systems. And I've been working on silicon carbide devices and circuits for more than 30 years. The outline for my presentation is I'll give a little historical overview of semiconductors and silicon carbide. I'll then tell you about the different commercial silicon carbide and gallium nitride devices that are around, and I'll explain how they work, at least in sense of what is the high voltage advantage. But I'll also put up the silicon contenders, the silicon superjunction MOSFET and IGBT. That's still going to take a big part of the market. I'll mention some future devices, and then I'll come to the cost calculations a little bit. I'll mention briefly extreme environment electronics applications of wide band gaps before I conclude. So, first of all, I want to remind you that this year we should celebrate the 75th anniversary of the transistor. It was invented December 1947, but it was publicized in June 1948. So we can basically celebrate both last year and this year. I think it's such an important invention. But these were made in germanium, later in silicon. For us power guys, there are more important inventions, I think. Silicon carbide, we always talk about the roots being in Sweden. Jöns Jacob Berzelius. Not only did he discover silicon, but also silicon carbide. In between, we have the bipolar devices from Bell Labs, the silicon MOSFETs from Bell Labs, but also the silicon carbide MOSFET came up in 1966. Now, remember in the 1970s through the 1990s, all we heard of was that gallium arsenide is going to take over all of silicon electronics. Didn't happen. Why did we think so? It had an excellent electron mobility, and that's it. In the meantime, J. Baliga made several inventions that are more important for power devices. He invented the JBS diode, I'll come to that, also the IGBT, and now later he's announced a new device, and I think we should look at that one as well. But in between, the superjunction concept was patented, and that one is still around. But we shouldn't forget the commercial interests. The perfect packaging for a silicon carbide MOSFET is, of course, a Tesla Model 3 inverter. This is what suddenly put new energy into all of silicon carbide industry, and it led to ST landing a huge contract and then buying Norstel and more of these acquisitions that Michael showed in his presentation. So as Tesla said, well, we have to go up in battery voltage size, otherwise the cables will be too huge under the seat for the driver. And going up in voltage, suddenly the silicon carbide power MOSFETs are a perfect fit in their range of breakdown voltage. And I'll show you why. But first, let me remind you that power devices are vertical devices. You take a silicon wafer or a silicon carbide wafer, you cut out the dies, you have one contact on the front and one on the back. The on resistance is inversely proportional to the area. So you can always get a low enough on resistance in these devices by just making it larger. But that costs. And this is the dollars per amp that comes back in these discussions. So, wide bandgap semiconductors. Which ones are there? There's silicon carbide and gallium nitride. Those are the main ones I'll focus on. But there is also gallium oxide and diamond. Now, just the wide energy bandgap doesn't really tell us the story why it's such a great material. We should look at the second line in this table, pointing out the critical field. And I want to highlight in silicon, it's 0.3 megavolts per centimeter. In silicon carbide and other wide band gaps, it's at least 10 times higher critical field. And this is the key material advantage. Because any power device, and I'm taking the power diode as an example, has to work in two main modes, off state and on state. In the off state, a region of the device has to be depleted. It has to be low doped, and it has to be wide enough. So the breakdown voltage depends on both the width and the doping. But then the device switches on. Now all of the current has to go through this low doped wide region, and the on resistance depends on the same two parameters. There's a trade-off. And perhaps you've heard that the on resistance is proportional to the breakdown voltage squared. There's a trade-off between breakdown voltage and on resistance of power devices. And I'm going to show you how we calculate this. But this means that for power devices, we select the lowest possible breakdown voltage for our design to also keep down the on resistance. But can we do something to get lower on resistance by switching materials? Yes, we can. So this is a complicated slide. This shows the electric field versus the depth in the same p-n diode I showed you before. This is the anode on the top of the wafer. This is the low-doped drift region that's going to support the electric field, and this is the cathode and substrate of the backside. And if we make a non-punch-through design, meaning that when we reach breakdown, the critical field is reached exactly at the p-n junction. This is where the electric field is the highest. The width needed needs to be 2 times the breakdown voltage divided by the critical field. So for silicon, certain width; for silicon carbide, 10 times shorter. But that's not all. If we need to support this breakdown voltage, we can calculate not just the width, as here, but also the doping needed to support this electric field. So for a smaller region like this, we put in higher doping compared to this one. And as you see in the equation, as the critical field goes up, the on resistance also goes up. So from physics, we can calculate that we need 100 times higher doping and 10 times shorter region. That all adds up to a lower on resistance, because the on resistance can be calculated from the depletion width and the doping. And using these other relations on this slide, we find the final equation saying that the on resistance is proportional to the breakdown voltage squared, but inversely proportional to the critical field cubed. So just 10 times better critical field leads to almost 1,000 times lower on resistance for the same breakdown voltage. This is the great advantage of a wide bandgap semiconductor device. 1,000 times lower on resistance. But the on-state voltage of our device, our diode or transistor, not only depends on the on resistance, but also on the built-in voltage. So the total on voltage has the built-in voltage and then the voltage drop across the resistance multiplied by whatever current we want to push through. So for silicon, built-in voltage is 0.7 volts. For silicon carbide, 2.5. And for any other wide bandgap, it will also be higher. This is a disadvantage, that we have a large built-in voltage. The total on resistance, we need to also figure that there are contact resistances, but the main part that dominates is this depletion region, the drift region, and in some cases, the substrate. Even though this is higher doping, it's also much thicker than this layer. So both of these two need to be taken into account. And to give you an idea how to calculate this, also I should point out that we normally think of current density rather than current. And that's because, again, we can always increase the chip size to get lower on resistance. But typically, we want to push around 100 amps per square centimeter. And the specific on resistances we're going to look for are in the milliohms times centimeter squared. I'll show you this in the next slide. But this means that the on resistance calculation is normally done with the current density and the specific on resistance. Because if we want to compare two devices, we want to compare for the same area, because at the end, the same area will have the same cost in wafer manufacturing. So then we come to this plot that you perhaps seen sometimes, where we have the specific on resistance on the y-axis logarithmically, and the breakdown voltage on the x-axis logarithmically. So remember, we are comparing devices for the same breakdown voltage. Say a few kilovolts. The blue line up here is silicon. So for a few kilovolts, this one has 100 milliohm centimeters squared. Multiply that with a current density of 100 amps, and you get 10 volts. Whereas for the silicon carbide device, having 1 milliohm centimeter squared and 100 amps is just 0.1 volt. So it is about 400 times lower when we take into account the mobility and the dielectric constants. This equation from the previous slide is called the Baliga's figure of merit if we look at this final part. So these are all material constants, and we can compare different semiconductors using this equation. So let's look at the commercial silicon carbide devices. First, we have the diode. So we said that the built-in voltage for a silicon carbide diode is 2.5 volts, and that's way too much. But the secret is that any silicon carbide diode you buy, well, sometimes they'll say, okay, it's a Schottky diode. With a Schottky diode, you can put a metal up here, and you can bring down to whatever voltage you want, but typically around the same as a silicon diode. However, in this figure, I plot current versus voltage. For our PN diode, we have a higher voltage drop compared to the Schottky, but a much better reverse characteristic. The Schottky diode is leaky because it's just a metal on top of the N-type semiconductor. And the trick is called the junction barrier Schottky that Baliga invented, sometimes called the merge pinch Schottky, where we insert P+ regions that will help. So in the reverse, these P+ regions are depleting this region, just like for a PN diode. But in the forward region, the Schottky diode is injecting the current with a lower voltage drop. So any silicon carbide diode you buy will be what's called a JBS or MPS type diode. And they're available in the range of 600 to 1200 volts. Then we come to the power MOSFET, the switch that we all like. So it's very similar to a silicon MOSFET, except that the doping is not diffused. It's available in even higher voltages at this stage. And the ohm resistance in this case is slightly higher if we look at it, because the current has to go from the drain through this low-doped region, through the channel, and up to the contact. And depending on the exact design, there's also a JFET pinch resistance right here. However, there's no built-in voltage, so we can make the resistance as low as we want. But what about silicon? How come silicon is still around? Well, the silicon DMOS, the basic concept, is good, but at higher voltages, we can make superjunction devices. In the superjunction, this low-doped N-type region is replaced by strips of N and P-type doping. In the reverse, they totally cancel out the charge, they balance out exactly, and deplete. But in the forward, these have higher doping, and therefore the ohm resistance is lower than the equation I showed you before. We also have the silicon IGBT, where we replace the N-type substrate with P-type. In this case, we can inject holes and electrons into the low-doped region, and we can reduce the ohm resistance by 10 to 100 times. And this way, the silicon IGBT is also better than the basic equation I showed you. Then we have the gallium nitride heterofet. It's not a MOSFET in the same sense, because the channel is not an inversion channel of electrons. It's a 2D electron gas, which means that the mobility can be much higher. So this is an added advantage for gallium nitride. Another one is that gallium nitride can be grown on 8-inch or larger silicon substrates. So the substrate cost can be a lot lower. But it's a lateral device. It does not push the current straight through the wafer, but rather travels along the wafer surface. This means that it's a bit limited in current handling, since for a vertical device in silicon carbide, the entire top area is used for current transport, and the width referred to is this depletion width, whereas in the gallium nitride device, the depletion width is between the source and the drain, and the cross-sectional area, well, it's the width of the device, but it's only the thickness of the 2D electron gas, which is much smaller. So when we take these into account in the same graph, we now find that this was the silicon theoretical line, but both the silicon IGBTs and silicon CoolMOS is better than this prediction. However, silicon carbide MOSFETs and gallium nitride FETs can push this ohm resistance even further thanks to their wide band gap. However, silicon has a lower cost. Other devices that could come up, well, the Baliga pair combines a wide band gap silicon carbide JFET or MESFET or a gallium nitride heterofET with a silicon MOSFET. This is nothing new, but it hasn't really taken off. United Silicon Carbide, nowadays Qorvo, has tried to market this device in about the same voltages as the silicon carbide MOSFET. And then Baliga's newest device, the BidFET, the bidirectional FET, is really two silicon carbide MOSFETs pushed together, and the two drains are removed from the device. Instead, you have two sources and two gates. So look out for this one, it's fairly recent. I also wanted to introduce PECTA, the Power Electronic Conversion Technology Annex from the IEA 4E, because so much energy goes through power electronics in every stage from production through transmission and then into our devices. We need to push the efficiency of all power electronics to 95% or better. The wide band gaps can offer a reduced cost, but at a higher component cost. It's really difficult to see that the silicon carbide device can become cheaper than the silicon device. But if we take into account the energy efficiency, pushing down a few percent, halving the losses, the cost of ownership can be better for wide band gaps. However, in recent designs, it's also found that wide band gaps can be pushed to higher frequencies. And in this case, even though the cost is higher for the switches and the diodes, all of the inductors and capacitors can be made cheaper. So the total cost for purchase of this system is now lower than the silicon one, without taking the energy savings into account. Higher operating temperature, yes, silicon carbide can work up to 600 degrees C. We've seen that in integrated circuits, but it's not really a selling point for silicon carbide power systems. You don't want to run them this hot. Radiation hardness, well, this is mostly for space applications. Radiation hardness is much better than silicon, but a typical car will not experience this. So in conclusion, one vastly improved material property is not enough. Compare gallium arsenide and its mobility, silicon carbide and its critical field. We have to take into account that if the device cost cannot be beaten, system cost or cost of ownership has to be there. If not, put into a Tesla where you can put any price on it. And extreme environment properties are really difficult to take advantage of, but I think we all can agree that wide band gap semiconductors like silicon carbide and gallium nitride are here to stay. Thank you.
Thank you, Mikael. Do you have any questions to Carl Mikael regarding this? Yes. Could you repeat
No,
the
it doesn't have
questions?
it doesn't have to do with the carbon density. It has more to do with the lifetime of the material and how quickly you can turn off the device after it's on.
The question is it possible to stack lateral systems?
What the gallium nitride industry is trying is to make them vertical, just like the silicon carbide. But it is difficult to get the 2D electron gas on a vertical channel.
Repeat the
So
question.
the question was about carbon nanotubes. We can discuss this in the break. But I think those have been ruled out since long, just like diamond.
Thank you very much, Carl Michael. And now we have the first presentation from a company that's here today. We have Hitachi Energy and Mohammed Nawaz. And we are very glad to have you here. So now we have the presentation on. The floor is yours.
Yes, thank you very much. Well, okay, I think maybe little is left for me for talking about semiconductor devices in general, but I will focus more on the power electronics parts, meaning that why we do power electronics and how we do power electronics. I am Mohammed Nawaz. I belong to Hitachi Energy Research. Let me introduce a bit more about Hitachi Energy. It's a part of earlier ABB, I should say power grid division of ABB, namely the corporate research. So we are a total of 38,000 employees right now. Our footprint is visible in almost 90 countries of the world. We have a lot of sales employees and R&D guys. 4 business units, namely the grid automation, high voltage products, grid integration, where I belong to, and transformers. We are offering, our customer base is associated to 3 segments: transport and infrastructure, industry, utilities. Our offerings are services, software automation, systems, and discrete products. Our footprint is equally visible in 3 areas: Asia, Middle East, and Africa, America, and Europe. Let me ask myself that why we are doing research in power electronics. Very simple question. We have the 4 major drivers here. I should say the mega cities. Our world population is gradually increasing, and we see that the people are moving from countryside to the big cities. And at this stage, we have more or less over 25 cities of the world we used to call mega cities, even 30s, I should say. Then we are expecting the faster electrification growth. At this stage, more or less 675 million people on this planet are without having access to electricity. That means 8-9% of the total world population. So we should act faster sooner than later. Then we see the explosive growth of EV charging infrastructure. That's another big market driver here for us. And not last but not least, we should engage ourselves more, increase renewables, because we must contain the carbon footprint here. You can see here the main contributors in CO2 emissions here. So the key message is, yes, secure, environmental friendly, and affordable energy supply is central to everyone. Then we have a long list of challenges here: energy production, energy transport, energy efficiency improvement, renewable energy utilization, and above all, we have very limited energy resource base. If you see on this slide, on the left side, we have world electricity demand by sector. I think Mikael have shown it a bit, but maybe in the different format. So you can see the electricity demand is going to be double from, let's say today, 2020 and onward. And most of this is the industrial segment, residential and commercial segments here. So this electricity demand will be more than double from now onward until 2050s. And this rising electricity demand means that it will outpace the economic growth, mainly due to new electricity consumption categories. On the right side, you can see here the conventional means of hydropower, for example, or oil-fired. These electricity generation sources are gradually going down, and the renewables will take the lead, and they will go on with more expanding role and more dominant role from now onward. So by 2019, we have 26% by renewable energy sources, and until 2050, we expect 82% by renewable energy sources. Then here, it's a very interesting slide. Well, power electronics is one possible form of conversion process. Either you can go from AC to AC, or AC to DC, or DC to AC, or DC to DC. So all these red dots means the presence of power electronics in various parts. Starting from the generation part, you have the more traditional power sources here. Then you have the wind, you have the pumped hydro, where you can generate the electricity when you need, and when you don't need, you put water in, and the reservoirs. Then you have the more solar PVs and other hydrogen and wind segments here. Then you have the transmission process here, from generation to transmission, HVDC, high voltage DC transmission here. And then you have a large industrial and commercial segment here. So you can see here the different end usage of the power here in transport, e-mobility. You have battery energy storage, residential and commercial segments. So all in all, I should say that at this stage, maybe 30% power generation is associated to the use of power electronics or power semiconductor devices. And this trend will keep going on, I think 80% maybe in 2030 or even more. So power electronics is enabling technology, revolutionizing the world's future energy system. That's the key message here. Then I just listed very few of our historically ABB products, but now we have the Hitachi Energy. So the left part, this area is more ABB now, because we have been bought up by Hitachi. And this part is the Hitachi Energy here. But I just put it here, very few products here. So you can start with the low power segment, where we have few kilowatt here. So you can see here the EV charging infrastructure here, both low for cars, buses, trucks. So you can charge them overnight, and you can use them with zero emission the whole day. Then you have a long list of industrial drives. It may be AC drives, it may be DC drives, plastic industries, metal industries, food and beverages, and a lot more. Then you have the traction converters here. Then on the high power side, we have flexible AC transmission systems and high voltage DC transmission system. These are our mostly the sweet spot of Hitachi Energy products. So large portfolio of high power converters for different applications, from few kilowatt to gigawatt range. So this is our should I say, the offering from the semiconductor point of view. I just put it here. Some you can see physically, you can ask questions. So on this side, you can see a stack pack, our loving baby here, mostly used in HVDC systems here. That's about 2 kilo ampere, almost I should say, and 2 kilogram as well. It's very bulky and heavy. It's sitting on the table here. Then we have the varieties of thyristors here. Then for low power, 62 pack and low pack semiconductor modules, we have IGCTs here integrated with the gate drive units here. Then on the new players, new market entrants, we have both silicon and silicon carbide. We used to call lean pack. You can see here on the table. Then we have a new product, silicon carbide road pack for automotive industry here. Then we are going to introduce very soon. I'm working on this SiC FlexiPack modules under development. You can see the footprint here on the table. Then we have a long list of high pack modules with different voltage classes from 1.2 to from 1.7 to 6.5 kilovolt, and with different current ratings. Then I would like to show you the complete, because it's not more conventional, it's more tailor-made for transmission applications. So you start from the IGBT chip, you have silicon wafer here, you put several IGBTs in chips in parallel, we used to call sub-modules, and then you put several sub-modules. In a bigger module, we used to call power module. That's single IGBT composed of number of transistors and diode dies sitting inside. You can see on the collector on the top side and emitter plate on the bottom side, and then you can see here the gate terminals here. So it's 4.5 kilovolt, 2 kiloampere, already in the field for several years. Then we make it in circuit topological configuration. It may be half bridge, it may be any other topology, full bridge. You put two IGBTs over each other, top high side or low side, and then you put gate drive unit across each IGBT to turn on and off the IGBTs here. And you can see the physical footprint of where you have 8 IGBTs, 2 times 8 IGBTs and power drivers there. Then you put the cooling stuffs and fiber optics communication around for control purpose. And then you have the converter on. So at the end of the day, you have a big hall of this size, or maybe 2, 3 times of this room, bigger than this. You have the wall hall. You can see here the top side and the bottom side. So the AC point is this one. So that's the overall, our product which we use to sell for HVDC systems. This is what we are offering here. You have the voltage source converter on the left side. You can see here a lot of IGBTs and drivers here. And this is what we are using, the 50 to 3,000 megawatt power semiconductors or IGBTs here. And then on the right side, we have the HVDC classic, which are the current source converters. Here we are using the thyristors here, the power semiconductor device, and we have DC voltage up to 1.1 kilovolt, 1100 kilovolt, and power range up to 12 gigawatt. So these are the two common offerings which we use to sell. So why Hitachi Energy? Because it stays number one, 60 years of HVDC experience, 120 projects worldwide, and 70% of all VSC HVDC links are associated to the Hitachi Energy. Okay, from the semiconductor point of view, I think Mikael and Bellman has fairly said and well said. Okay, so we have the collective wisdom is this: we have 3 materials there: silicon carbide, and gallium nitride. So gallium nitride, probably you can see here, maybe 650 volt lateral hands, low medium power with high switching frequency. I put it here, low power and high frequency here. Then you have silicon carbide is expected to replace silicon in many applications, offering new targeted solutions there. So you have 650 volt up to 10 kilovolt. Vertical devices, high power, high temperature, high switching frequency. IGBT is yet to appear. Silicon is more mature, cheap, rugged material. So wide band gap semiconductor devices now stay at the doorstep of market to offer new intelligent power solutions. So you can see here the market size as a function of system power. So we expect that we are in a transitional phase here. So silicon carbide will take the dominant role, but higher power you go, your market volume shrinks. Smaller, large market volume, but tougher competition at low power range. So Hitachi Energy playground is on the corner. So you have much competition on low power. You have moderate competition here. So we stay on this corner in terms of voltage and current. So the converters, we have a lot of expectation. We expect the efficiency, high efficiency. We must comply with the IEC standards. We must have availability and reliability here. Footprint, customers ask to have lower and lower. We should have zero maintenance. We must expect to adjust the ambient temperature. We should expect intelligent functionality. And of course, the cost is lower. But you cannot have, for optimal solution power system, you cannot have all the variables to optimize simultaneously. There are trade-offs here. You have the switching frequency. You can go up switching frequency. You probably may reduce the footprint here. It might have the complexity, integration, redundancy here, life cycle cost. So there are many, I should say, the trade-offs here, but it's the customer's choice, which always have a choice for most important variables for certain applications. So tougher customer requirements, challenge converter manufacturers. So the key challenges here, yes, for assuming silicon carbide, we expect the shortest possible time. We should expect lower losses, true, but how to design a system to handle high dV by dt and di by dt. We need high performance controller because we are switching much faster. That may be the last item. So we should expect faster protection scheme as well. And since we are talking about very high dV by dt and di by dt and high current, so you have a metallic parts there. So you have associated stray capacitance, and then you have to think about the EMI because you are switching very fast here. We should expect higher blocking voltage using silicon carbide, but it might introduce some less redundancy, how to handle faults. Insulation might break down. You have the higher junction temperature, and you have the thermal fatigue here. And power integration, since in big power converters, you have a lot of other components, so you make it possible to compatible with other components like reactors, sensor, capacitors, transformers. I think I should stay here, maybe the last slide. So this is what I should see from the silicon carbide point of view. Thank you very much because of the time. So
thank you. I have a short question, or perhaps very long. It depends on how you want to answer it. I mean, you are a global company, and if you look at the global world today and the globalization, we have seen in a very short time a switching towards more protectionism and so on. How do your company deal with that?
Protection?
Yeah, the protectionism regarding the ARR Act in the States and EU and the ships joint undertaking and the war in Ukraine and so on. How does your company, since you're a global company, how do you deal with the new challenges regarding that?
I think some answers probably are not within the scope of my talk, so to be honest with you. But yes, we stay with the globalization. We are well integrated. We are somewhat supporting, I should say, some way the Ukraine war as well. But this is what I think we should say. So.
Okay. Some other questions? No. Yeah. Mikael, you take mine.
So, Mohammed, great. When you hire people, what's the situation today to get the right talents?
I think
How much do you need from us here?
As maximum as possible. If you see as of today, we need a lot of people here. So there is desperate shortage of skilled human capital in power electronics area. That's I can guarantee here.
I have a question.
Yep.
Like 20 years ago, would you have hired Elon Musk if he was applying for a job? A question, would you hire Elon Musk if he applied for a job 20 years ago?
We can hire him. Why not?
Okay, thank you. And now I would like to present Mikael Hjort. He is from the Electrification Hub. And he will tell us more about how electrification drives the electronics industry. And then we will have a short, during his session, we will have some discussions between you all. So I leave the word to you.
Thank you.
Thank you.
Thank you very much for having me and having us. I'm gonna run through you. I call it the pre-launch of a data-driven analysis. What we've done is we've started a project where we work with a business intelligence tool, and I'm gonna present how we're doing it. And this is kind of a pre-launch. So what we're gonna do, as I said here, we're going to have a discussion, and I want your input on how can you use it, what's the benefit for you, and how do we continue developing it. But first, why do we do this analysis? One part of it is because we see that there's an accelerating development, and with that there's a lot of discussion about how's the raw materials going, what's happening to components, what's happening in the battery field, and how's the infrastructure developing. And these questions keep coming up, and you have different analysis. So what we've tried to do is say, let's do this continuously and recurring, and then you can have a baseline for what's happening in the development. And we've seen several, of course, projections here today. The other thing we'd like to have it, and that's why we want the discussion here, is we want to have the analysis as a basis for action. So what can you use it for? Is there opportunities as a company to go into? Are there research opportunities where you can collaborate and so on? And how do we continue? So that's what I'd like to talk about. First, shortly about the Electrification Hub. We're an innovation accelerator, and we have a number of founding partners in the middle. So nice to hear Hitachi, and we will hear some others later on today. And we are focused on accelerating electrification, primarily heavy transport or heavy vehicles. So as you see, Epiroc, Volvo Construction Equipment, Alstom, and so on. But they're also combining the strength we have mainly in Mälardalen, where we connect the energy competence with the components all the way down into vehicles and so on. We work in 3 areas. The first one is what we call scaling innovation. Fascinating with this pointer where you point at the computer. But scaling innovation, we don't do research ourselves, but we try to see what's the research doing and can we put it out there. And as so many things are happening in the market already, we try to work with demonstrators. So where we put vehicles out into the field, and many are doing that already today, together with charging and so on. What happens then? How do we balance it towards the energy grid, and what happens? We work with the business development, so startup and larger company collaboration. And some of you have had ideas here and talked about startups, and if you have companies that are interesting, could be anything within the electrification field, because there are so many things happening, and we try to make real projects between larger companies and smaller companies. And of course, we've talked about the scaling, industrialization, so we try to support scaling of production also where possible. And finally, of course, competence and attraction. Today there's a scarcity of competence, so we try now to see, can we do campaigns internationally to attract talent to come to Sweden? And also, how do we make them stay? How do we retain them? And how do we grow and develop them through reskilling, upskilling, and professional networks? So briefly about that. So what we've done is we've basically mapped up the electrification value chain, and on the left-hand side, you see some of the batteries and raw materials here. In the middle, you have more of the vehicles and applications. And on the right-hand side, you have the infrastructure where things come out into society in terms of grid applications, charging infrastructure, and so on. And we focused on the areas which have a box around it, the green boxes. So we've, for example, the OEM process, we've skipped at this point. We think that there's a number of bottlenecks within raw materials, within components, and so on, that we started out in that field. And also then all the way towards charging infrastructure and the development of that. Just this, I thought when I came here that I would have complex pictures or slides, but I'm in good company, I think, here. So this is just to give an idea of the database we're using. Is basically we pull data out of a number of sources, and then we aggregate them, which means that we today can basically push a button and get the full report out any day of the week. And but we've said that we're going to do it quarterly. And it's based on public data. Some of it is more, how should I say, not so open, but it's still data, a number of data sources that we try to use. And they evolve and get better, and then we try to change it too. But it means that we can do recurring reports. It's not a one-time report, and then we have to do it again and change everything. But we can continue. And at this point, we've said that we're going to try to have a slightly different focus depending on which quarter we're in. So so there's going to be full report in Q1, focus on electronics Q2, batteries Q3, and then we'll see what's Q4. And if you have any input on that also, please let us know when and where it would be good for your usage. The full report, and I'll just give you a glimpse of it today, is about 60 slides, it's 60 pages, and they're full of data, and it covers these six areas. One of it is about macro aspects. Some of them are, of course, what you talked about now, globalization and protectionism. Others are about raw materials, cell and patent applications, giving the importance for electrification about batteries. Electronics and semiconductors are a good portion. Then we have product technology and charging. And I'll try to run through some of them. And there's two components that we're looking to add already now. One is competence, because competence seems to be, like I said, lacking in many fields. So how do we get that connected to this? Of course, you already know several of these things. There's a number of bottlenecks now. We talked about the geopolitical risks on the macro level. I'll come back to that, but you both have the European regulatory framework and the Inflation Reduction Act. That's having a big impact on movements in the industry today. On the cell, you're looking at the large-scale LFP production, and then you have the US-China trade war, basically. And here you have a lack of competence, which is limiting. So we've had a European perspective, I should say, primarily at this point, but where it becomes interesting, we'll add in. Thank you. Thank you. So I'm not the expert on this, so I'll just give you a glimpse of some of the materials we have. This is on nickel, and so these are, each of the raw material slides will be similar. So here we have the demand, and you have the supply. And in specifics, this is nickel, and Indonesia has been increasing their production, which means that there's an excess capacity of nickel today. But as we move towards the mid-decade here, there's going to be increasingly focus on emissions and so on, which makes the Indonesian nickel not suitable, or they have to increase the quality of the nickel. Otherwise, recycling of materials will take the role of their capacity. This is another raw material, cobalt, where you see the limited mining capacity. And of course, you've seen the reduction of cobalt. Oops, sorry, I jumped back. In a number of applications. So that means that it's going down, and also you can see the supply going down as we move forward here, and then you're going to see other ways of getting cobalt in, but it's going to be used for different things than EVs probably, because it's being reduced in those applications. This is lithium. Another important, which is of course skyrocketed. There's a number of increasing capacity building in terms of mining and so on, but it's also going to be an oversupply then here also when we get recycling and bringing them back out into production. This is a picture of where the electronics industry production being put out, and of course we know that there's focus in these countries down here, Germany, France, UK, and there is a increasing production. I think I'm using context. I couldn't read the small number, but it's about 2.5% of aggregated growth from 2023 to 2027. And of course, there's going to be a number of production projects based on that. This is the projections for electric motors and generators. And because there's the Chinese supply of basic components, magnets, into the engines, they're going to keep a good majority of the market, and the European market won't, or the European supply won't grow as quickly, or being basically reduced. You can see it's going down over time here. This is a projection over electronic components, and this connects, of course, to the CHIPS Act. I said I wouldn't talk about the CHIPS Act. We've gotten really good presentations about that today. But that also means that there will be some increased production potentially, but still there's so much growth in other areas of the world. So this prediction doesn't say, or our prediction doesn't say that the European part of it will increase that much. But the market will continue growing. If you look at the market for semiconductors, for example, as we've spoken about today, you also see that there's been a cooling down of the market at the end of last year, which has been a reduction. Some of it is driven about usage, and of course some of it is driven about this shift to other areas, which is shown here, I think, where we've seen, of course, during COVID, a lot of it went into computers and communication devices because everybody was working at home. Now, as that growth is slowing, it's moving over to other sectors, such as automotive, electronic areas, and also the energy field, consumer electronics, industrial robotics, and so on, where we've seen a shortage, of course. I mean, several of the companies in this area has had shortages for a long time, and which has meant that the delivery time has taken very long. And this is planned investments into battery production. You can see that there's a number of projects plotted out here. But of course, with the Inflation Reduction Act, which reduces the payback time to about a third compared to European predictions, there's going to be a move towards the US potentially, unless we take action to use it. So some of these might very much well just dry up, and we've seen some of them, like Britvolt and others, or Britvolt, that collapsed, and we'll see what happens. And finally, this is charging infrastructure in most in Europe, and you see that in most parts of Europe it's very immature. In some parts in the middle, you can see it's fairly developed, but still, with the projections being set out for Europe, there's a huge demand, and that's going to be, of course, driving components. It's going to be driving production, and we see a number of both investment partners going out, setting up charging infrastructure, energy companies investing, and of course we've seen companies like Traton and so on creating joint ventures to get chargers out there. That's what I'd like to run through, and it's just to give a glimpse of what the report has. There's much more in it, but based on this, I'd like to propose that we have a discussion here. You can just turn to the people around you, talk 2 and 2 or 3 and 3, and around 2 questions. One, given that the analysis that you've seen, the projections, it could be, and you've seen some of it, what types of initiatives or projects could this inspire? Are there things if you're working in a company, things that you're looking at, development projects, investments you're looking at, other markets? And the other thing is, in what way would you like to work with a report like this? I mean, we're making it accessible for us, so we are interested in how would it best be used, basically. So with that, I thought we'd just take 10 minutes, maybe. If you turn to the people next to you and just start talking. Let's sounds like you've had a lot to talk about. It sounds perfect. Yes.
Yeah, and we thought that I will walk around here and pick up some of your discussions. So I will just take a tour around the room. And while I'm walking, you can tell us where we will find this report afterwards.
Absolutely. So we will, as this is a pre-launch, we're going to launch it in a webinar in mid-June, approximately. And then it's going to be accessible both on our website and on Business Sweden's website. So we'll send out information to all of you, how you can reach it. And of course, if you're interested in more. Yeah, sure.
What's your ambition with all this? If you have a magic wand, what to make you happy? What do you want to accomplish, short term, long term? With all this, is it something that you want to see another North Pole in front of you?
Yeah.
The question is, what do you want to achieve long term or short term with this report?
I mean, of course, that's what we like to do. We'd like the reports to be a catalyst of getting things, people wanting to invest in this, people starting companies in this, and also seeing where would they go with it. So that's, I mean, we want to accelerate electrification. That's what our ambition is, and anything that kind of drives that forward. That's where we don't want to just make a report. We want to have a discussion around it and see what's the use to you with it. Is it useful or not?
Okay, the first stop. Your discussions. Okay, who wants to take the microphone? Since it's Norwegian's last day today.
We discussed about getting like influence from what's going on, so we can advise our customers to give them good advice on where to go and what kind of components to use and that kind of questions.
To just give a view, this is happening, and this is where our things could support you in that drive. Okay.
We pop up here.
So what is the expectations from your industrial partners that you have in the electrification hub concerning the very, let's say, the analysis possibilities that you provide? What would they expect as an outcome? Thank you.
What they expect as an outcome? I mean, yeah.
From the reports after the web seminar, and when you have finalized the fine-tuning of the presented material, what would they expect to? I could rather say, how would you expect them to use the material? Thank you.
Mm-hmm. For us, I think it's been. That's why we want to do it recurringly. So for us, it's a way of both combining the R&D plans that's being going on, and also rollout plans, and see, are there areas we should focus on more? Are there things we can do together? So for us, it's we're expecting it or hoping for it to be a useful tool, not to discuss together around and see how do we combine forces to address this. We've talked today about combining forces, not working against each other, and I think we need to do that.
No comment? Do you want to comment down here? We continue.
It was actually a comment from Ganesh, but I thought it was so good, so I took the mic. No, but it was a lot about the data for selection of supply chains and so when we build this business going on. And I think, hopefully globally, but at least in Sweden, we talk much about the sustainability aspect. How will this data be able to help companies growing in the aspect of sustainability?
But it's a good point. That's actually, I said there was two areas: competence and sustainability is the other one. And on one part of it is, of course, sourcing of materials and so on that we've mentioned. That's a key point. Like Indonesia, we talked about, and we've also seen some of the others. But also components. Where can we find the supply chain that's different to what we have today?
The other question is then how?
How?
Yes. should everyone know which country to go to, or will the report support people who are not so educated in the area of sustainability? Do you need to know that Indonesia is a good or bad country to go to, or how does the report support?
That's a good point. Maybe but of course, yeah, if you change it, if you switch it around, yes, the data in the report can provide that analysis. So maybe that's a part that we should emphasize much more. To have, like, because you see in some of the pictures or some of the analysis that comes out in terms of emissions and the component and other types. So it's a good point. Maybe that should be emphasized much more in using data.
Okay, interesting to see what kind of parameters you have accessibility to. So if I have the university perspective again and a supplier of talents, maybe that would be something that you can plug into your model. What is the industry looking for, so we can understand what is the demand for talents. That could be one option to add this. And so you have quite a number of commercial actors, you have some regional actors, and I'm sure you want something yourself. Not just having support from them, but together within your system, I guess you have a model that maybe was not so clear here. What do you want to show? Mm-hmm. If you want to show that the electrification is the most important thing, I guess you have to also provide the data based on the available numbers that are out there and show that, okay, Vinnova just said we need help with the arguments to get more money from the government, and I think that's something important with your data sheet here. Mm-hmm. How you can do that, but it has to be a more sort of proactive search for what data do you want to show, not what data are there, but what you want to show, and plug in the number of skilled people that you need on various levels. Thank you.
Yeah, that's a good point. Yeah, and that's, we've also spoken about like startups that go into this field, just getting projections of where some of the areas are moving. Also a more proactive way of using the data, not just showing this is the way it is, but also saying we're going to take a part of this market or so on. Yeah, perfect. Thank you.
Okay, we had a little discussion. Sorry, we had a little discussion here on the sort of the global. You mentioned, I think, IRA in some of the, and I think made a comment that that would affect the analysis a little bit. So maybe we just had a comment that could include more of the global aspect of and the geopolitical aspects of what is happening with the supply chains because of the big funding programs that are going on in the U.S. Yeah, that was mainly, I think, our discussion.
Yeah. Excellent. Yeah.
Last but not least.
Thanks. You talked about battery. Please involve stationary battery technology also in your report, especially for storage time of, I would say, plus 50 hours. And how that develops. And not hydrogen-based, please.
Sure, absolutely. I think there's some parts of that, but we haven't seen it, but we could emphasize it or show it more.
Thank you.
Thank you.
A big applaud for Michael.
Thank you.
And now we will have lunch for 1 hour. So we will be back here at 5 minutes past 1.
Oh, welcome back from lunch. Hope everybody had an enjoyable and very networky lunch. So what we've heard this morning is that power electronics is very important. It controls kind of the electrical energy flow through the society. So last year when we had the Power Electronics Day, we had the goal of the should I switch? Hello? Does this one work? Yeah. So the goal of the Power Electronics Day last year was kind of putting the importance of power electronics on the map. This year, I'd like to hear a little bit more about the needs and the plans of industry. And that is something that we will hopefully hear about now this afternoon, where we have several talks from industry. And we're starting with Thomas from Scania. Welcome.
Yes, thank you. Yes, hello everybody. Yeah, I will give an view into different power electronic technology issues that we are facing in the vehicle design here at Scania. So yeah, we have great news here that the future is electric. To master the carbon and climate crisis, that's good news. Oops, sorry. So I will, here we can see our roadmap for introducing the electrical trucks into the market. That today we are in the beginning here. We have some little bit the lower range trucks out, and we are now about to roll out the larger trucks here that has the with longer range up to 300 kilometers. But the target is here that by the end of 2030 that we should have about 50% of the volume in electric. But I will focus on 4 different kind of technology challenges here that we are facing. One is the charging. We need to move up from the today's capacity of the CCS charger up to the megawatt charger to get more voltage and power. We have the semiconductor technology related to voltage levels of the system. And we have, regarding materials, we have risks in materials. For example, the battery materials, cobalt, lithium, graphite. But we have also neodymium that we have in the electrical mode, in the permanent magnets. And then the battery, to get the most of the battery, we have some ideas around that we are looking into. So first, some specs for the today's truck that is launched. That has a continuous power rating of 400 or 450 kilowatt, battery capacity of 600 kilowatt hour installed, but the usable part is about 460 kilowatt hours. And it has a range of 350 kilometers for a 40-ton version and a little bit less, 250 kilometers for a 60-ton. And this is now available for the CCS charging, 375 kilowatt. And that will take about 90 minutes to charge the truck based on that type of charger. So certainly we need more powerful charging. So we know that we have this megawatt charging system is being discussed and on its way that will lift the voltage to 1250 volt charging voltage and the current capability of 3000 amp. This was launched, some pilot was launched last year, and we have some demonstrator installation at Scania. But now I'm told that about next year the sub-suppliers of the megawatt charger systems will start to deliver systems. So it's quite timely with the rollout of trucks. Then in order to match this higher charger voltage, we need to increase the voltage in the vehicle. I should say today the battery voltage in the vehicles are 850 volts. But to meet the charger, we need to go up to 1250 volt and still meet a design which is compact, and we need to optimize the losses continuously to have good efficiency. Vibration is an issue because we can mount the driveline on the axle, that it's having the vibrations from the road. And we're also striving for increasing the amount of diagnostics in the system to monitor semiconductors and even gate drives. So this is a project that is within an EU finance project, PowerRise, that is addressing these issues. So it's a cooperation between university and some other companies. And regarding the inverter technology, today we use this, what we say, the two-level inverter, which basically have 6 semiconductors. So it can switch the electrical machine voltage between two levels. And today we are using 1200 volt silicon carbide modules here, because that's good when we have a battery voltage of 800 volt. But now going up to 1200 volt, we would need 1700 volt components. And these are not yet fully commercially available. There are some components coming in, but that's something we are looking out for. But alternatively, the converter could be designed as a 3-level, where you have each semiconductor here is replaced with 2 semiconductors. So you split the voltage step. When you switch, you split it in 2 halves. So you only take half the step each time that you switch. So then you can still keep the 1200 volt device. You also have an advantage that you get with a lower voltage step, you get less electromagnetic emission, less disturbance to the system. Then you can go further in adding more, increasing the number of steps. Here is a solution to have basically a number of 2-level inverters in series. And this can be combined then with an electrical motor with multiple phases. And then we have the most extreme converter, so to say, a multi-level converter, where the converter is modularized in many small converters, which each one is making a small voltage step, perhaps in the range of 50 volts. So here we can use silicon, 80 volt silicon in this kind of converter. So this is different converter that can be considered now when going up to 1250 volt to find the more suitable solution. That was one area. Then about the risk materials I talked about. This topic related to the neodymium in the permanent magnets. That's a rare earth metal which has a scarce supply. So there one can look into different alternatives for how to design the electrical motor without rare earth metals. So one can use ferrite instead as a magnetic material. Another option is induction motor, which Tesla have used in their first models, with an induction motor with a copper rotor to get good losses. Then one can have a synchronous motor with a wound rotor. And one can also have a switched reluctance motor. There are different options. what we have, one activity here, a master thesis project, is looking into this wound rotor design as one alternative, which is interesting. So the wound rotor would look like this, that we have a winding on the rotor, and somehow we supply a DC current to this rotor to provide magnetization of the rotor in order to then produce torque together with a current that we feed to the stator windings from the inverter. So the first question here is how to supply the current to this rotating rotor. One alternative is to have a transformer, a rotating transformer, where the primary winding is static, but the secondary winding is part of the rotor, so it's rotating. The more traditional alternative is to have slip rings. I mean, this is the conventional design for synchronous machines for large power stations, like hydropower stations, nuclear power stations that have this kind of generator. One could also have a capacitive coupling. So this is the traditional drive line that we have when we have a permanent magnet electrical motor. Then we have the inverter that converts the DC voltage from the battery to the electrical motor. If we have an electrical motor with a winding on the rotor instead of permanent magnets, then we have this rotating transformer, which we need to feed with the AC voltage. And then we need a rectifier, a rotating rectifier, so basically diodes in the rotors. So that is one area that is looked into. Here we have a test setup here with this. Here we see the rotating transformer with the primary and secondary. And then we just have some slip rings here to recover the current. So this does not include an actual electrical machine. So if we compare pros and cons between a synchronous machine with a wound rotor compared to permanent magnet rotor, one big difference is we have this, what we say, field weakening. A permanent magnet machine, when it is rotating, it is giving an induced voltage, so the output voltage from the electrical motor will be proportional to the speed of the motor. So when you have a high speed, you come to a situation where the voltage is too high for the inverter. So then you have somehow to weaken the magnetic field of the rotor. And that you do by adding extra stator current, you could say. But if we have control of the rotor current, as we have in a wound rotor synchronous machine, then you can reduce the magnetization through control of the current. So that's an advantage with this design. Yeah, in the overview comparing the different technologies, I didn't point out that, but there we can see that the wound rotor design is on a material cost more costly. The cost per kilowatt is higher than a permanent magnet. A permanent magnet is very efficient in a kilowatt or dollars per kilowatt. But by having more system advantages in the overall vehicles of improving controllability, and we also have a safety aspect that the permanent magnets, they serve as a constant energy source that will induce voltage when it's rotating. If we can cut off the magnetization, then we have a safety aspect that is in a better state. Then the last aspect here was the battery system, how to to get more use of the battery. And here, looking into a battery system that is modularized, so that we have, instead of having a complete chain of cells giving 800 volt, it's here modularized in modules together with semiconductors, so that these modules can be switched in and switched out based on an overall control objective. And then we can, for example, decide to connect many of these modules in order to reach a high voltage when we want to charge. But then when we are operating the vehicle in driving condition, then we could operate at a lower voltage, say 800 volt, and then we connect fewer of these modules, but keep permutating the modules so that we use the energy of all of them, but at the same time we only have modules connected sufficiently to give the 800 volt. We also get some inherent fault isolation possibility through the switches installed in the battery. So this is a way of utilizing the battery. So here we can see a view how this would, we have these switchable modules that the green ones are connected and the red ones are not connected. So it's permutated around so that all cells are used. Yeah, then another alternative of this modularized battery is to connect and disconnect these modules in a way so that we generate AC voltage directly from the modules. And then we can produce an AC voltage which is very much sinusoidal with a very small distortion. Instead of, this is the typical output voltage from a traditional vehicle inverter, which have high voltage steps related to the full battery voltage. So this would be then how the total system would look like if we have these modularized batteries, which gives AC voltage out. That here we connect the electrical machine directly to these modules. So in charging, we would have all the cells connected, and then when in the motor operation, they would share current. The two halves will share current through the electrical machine. So this have advantage in reducing the voltage electromagnetic emissions towards the electrical machine, reducing the EMC problems. But above all, it brings controllability to the battery system so that we can manage the individual battery modules to reflect the different state of health for different modules, that some modules needs to be treated a bit carefully compared to other modules to keep the overall system running. Yeah, that basically summarizes my presentation here of these 4 topics about the charging, the 1250 volt inverter technology, the rare earth-free motor technology. Important to mitigate the risks that about raw material supply that we heard about earlier here today. And this modularized battery system to really enhance the battery utilization and the state of health management. Yes, thank you.
Thank you very much. I have a question. You mentioned that you had a master thesis here regarding one of the topics.
Yeah.
And what do your company do to, regarding skills, and what does Sweden have to do to have more skilled people? Or what do your company do? The first question.
We try to have active contacts with universities to have link. I myself is affiliated with Linköping University, and other people have have contacts with other universities to keep contact and catch students when they pop up and or show interest.
Good. And what do you think Sweden should do? I heard the report yesterday wasn't too satisfying regarding the way young people read. And I mean, we have had also before the way maths, so is educated in schools. I mean, well, we lack a bit of competence in that. What do you think Sweden should do to have more skilled students?
I think we should increase this kind of hands-on experience. I fancy a lot that people really get in contact with equipment and stuff and build stuff and so that is something I think we are.
Good. Thank you.
Yeah.
Thank you very much.
Thank you.
And our next company is Siemens, and we have two persons there. We have Mahmoud Darwish and Lars Ivarsson. Welcome. The floor is yours.
Thank you. Good afternoon, everyone. My name is Mahmoud. I'm here coming from Budapest, from our location in Budapest, Hungary, where we are developing, designing, and manufacturing power cycling testing equipments and thermal characterization testing solutions. Today, I'm glad to be here with my colleague Lars from Gothenburg, Siemens Gothenburg. And let me start by motivating the topic for today. I chose this metaphor, coming together to catch the next big wave. As most of our speakers today discussed that we have tremendous growth in the power electronics industry and power electronics market. This is due to several drivers, the electric vehicles, electrification, and the higher demand of renewable energy. As also one of the speakers mentioned that there is a high demand nowadays for a more efficient, energy-efficient solutions. This involves using more power electronics for increasing the efficiency of the electricity converting and inverting. Since we are in Sweden, I would like to show some statistics about the Nordics region. Here, this is an infograph showing that Nordics are heavy power consumers. This is due to several reasons. First of all, it's cold, yes. They have a very cold climate. Second reason, I don't know if you agree with me, but Nordic people have very high life standards because they have money, so they would like to buy more appliances in their houses, in their garden. So these all appliances are using electricity and consuming more. So this is the consumption of electricity per capita, comparing the Nordic countries with the rest of the world. Increasing wind power generation. This is happening in Nordics as well. We see this is forecast from the Nordic Grid Development Plan that wind power is growing dramatically in this region, and Sweden is in the top. This all requires more developed power electronics for the wind turbines, converting electricity and to control the frequency and to integrate it to the electrical grid as well. Electric vehicles. We are using power electronics in most parts of the electric vehicles for controlling the motors, for the battery management systems as well, and in the charging infrastructure. The power electronics that goes to the electric vehicles has a lot of design considerations. The size, the weight should be at minimum, and this brings a lot of hassle when it comes to thermal management. We will talk about some solutions. I will briefly introduce some solutions we have for the thermal management testing at the end of the presentation. Here, I'm showing a typical power module design flow, where there are multiple vendors for schematic design, for layout, for verification, for CFD simulations, and integration between each stage of the power module design will bring some issues when it comes to the integration between a simulator or a software of vendor A with a vendor B when it comes to exporting and importing data or schematics from the circuit simulation to the thermal simulation. This is because of the multiple vendors during the stage. This brings a lot of design iterations, and this requires producing more prototypes during the design flow. This is something that recently Siemens was working on. Since we have the whole package of the design flow, then Siemens worked hard to integrate the whole solutions in one flow, where you can simply import and export data or schematics between each stage. This helps a lot to decrease the design iterations and to solve tremendous problems. Because in terms of power electronics, we said this is a very high or a very growing field where in a few years there is a new technology, and when it comes to the design, winning the time is very crucial. This is a study or a proof of concept that we run to one of our customers. We studied the design flow they have, and it turns out that normally there is 12 or more iterations or stages for the prototyping in their design flow. And this is around, this takes 12 to 18 months, while integrating the whole process to one solution. This is reducing the time and iterations tremendously. Here is a flow of design that Siemens providing from the first early step of customer specifications up to the integration in the vehicle. I would like in the next few slides to focus more on the life cycle testing, moreover the thermal testing, because this is what we do in our location in Budapest. And this is an example of a power tester that we provide or we are developing. This is used in a lot of manufacturing, car manufacturing companies and power electronic manufacturing facilities. This is a power cycling module that has cold plates in itself, and it's capable of power cycling for the lifetime estimation and the reliability testing. It's also capable of thermal characterization, where we get a so-called structure function that shows the heat flow from the junction to the ambient or to the cold plate. This results in a structure function that is constructed from thermal impedances and thermal capacitances. We have also a smaller device that is called Tristar-SI for smaller applications. It's also for IC packages, IC circuits, and it has very high accuracy. It measures or samples in 1 microsecond sample rate, and the temperature sensitivity is 0.01 degrees Celsius. If you will have any questions, we have it outside for demonstration. We can show it to you. And this is the end of my presentation. I'm happy to hear your questions.
Thank you very much. Do you have any short questions? Otherwise, the long ones will be taken outside.
Okay.
Thank you very much.
No problem. Thank you.
Great. And now we have entered the part of the agenda where you will have the possibility to have several aspects on the agenda that we are working on together with RISE. And the background for this work is when the program Smartare Elektroniksystem started. That is an innovation program that started 9 years ago. It was a work done before this program started that resulted in the first agenda for the electronic industry. And now we have asked RISE to do agenda number 2 for us, since we are having this, the innovation programs in Sweden, they are 17 right now, but they will be like 3 to 5 the coming years. And since we think the electronic sector is very important, but not so visible for most people, we think that it's very important to show the importance of this sector. And therefore, RISE has started the work with an agenda for the electronics sector, the second one. And I will give the word to you, Ursula. And we will have a small workshop here with a lot of Menti questions and discussions in order to catch up with the important issues that you want to bring up in the agenda. So here you will have the possibility to have impact on the agenda. And with that, I leave the word to you.
Thank you so much. Thank you a lot, Anna. So for the introduction to the electronics agenda work we are doing, and also the workshop we will have with you here today. So now, first then, we will continue with some condensed information about the project itself, how we are doing it. And then you will have the opportunity to get a really first version of the results that we have been coming up with so far, and that we also think that could be really interesting as well to share and get comments on. So this we will do, and to my help here, I have Helena Wiberg, and I have Adam Edberg, yes, Edström, sorry. And we will help through this here and facilitate the workshop together with you. So then after, when we have been going through a bit of the results here, we will have a Menti questions, some questions. Perhaps you have not used Menti before, but Helena will guide us through this. Yes, this is an easy peasy thing. But be prepared with your phones to be able to participate in that. And when we have done that, we will get the results up here immediately and check out what they are saying about what we think about things in here. And we will also have a small panel here, so we can get some immediate answers. So it's very direct, everything here. So we will have Anna answering in the panel, and Claes as well. And then I think we also will have Ganesh, yes, also here in the panel as well, yes. And then, of course, you will also have the possibility to bring up questions or say that they are wrong and you have other suggestions and they are in their bubble and, things like that. So we will be very happy to gather all these things to bring with us into the final work with the agenda to get everything together and help out with the strategy, so to speak. So what do you say? Are you prepared? Yeah, good. Then we go on here. So let's see. What is happening here? Now I got a little bit stuck here. What happened? Uh-oh. Am I prepared? That's a good. Yeah. Things happen. Let's see what we do. We do this once more, I think. Now we see my problem-solving capacity. Where is it? Let's see. We see how it's working when it's yes, and then we see so okay, let's see if I no. Why is it not? Det här var konstigt. Det här var jättekonstigt. Sorry? I det andra formatet kanske? Ja. Vi gör det. Gud vad konstigt. Ja, vi gör det. Det var lite konstigt. Men så här kan det ju bli i verkligheten. Det vet ju ni med. Vi kör upp här lite stort. Ja, vi gör så. Jag ber om ursäkt. Nu fick ni en liten paus. Tankepaus. Yes. Okej. Men då så. Då börjar vi lite grann bara med det övergripande. Sorry. Yes. Language. So the overall objectives and the prerequisites of the agenda. And that is that we will have an agenda, a strategy that will guide decision makers in the Swedish electronic industry. But not only that, it will also be towards Swedish authorities and national and international funding agencies and so on, so that we really can have help from this to improve, to really put initiatives and to really put forward our questions and what we need, so to speak. And the agenda should apply for the next 12 years from 24 to 36. And it will be based on the needs identified from Swedish industry and also the development potential. And for the, now you see everything here as well, live here. So, and also the potential for the electronics area in academia and in the electronics industry as well. So it is, try to wrap up everything and really get out the message from this area. So what have we been doing this is a little bit of everything here, but just so you get a bit of an idea of what we have been doing. So we have been talking to individuals, we have been doing interviews, where each interview is about 1.5 hour long. And that is people from, both from the industry, but also covering academia a bit and organizations as well. We have had 3 workshops that is on a group level more, a digital workshop where everybody could participate, on Teams, I think we had. And then we also have had an Optopub here in Kista. And then also, of course, today, to get your views on things here. So, and then also we have been using different tools. One that is not mentioned here, but very good, that I would probably, or perhaps you're using it already. It's the one up above there. It's a mural called, where you can all work in a digital meeting. You can work together on a big area that you can prepare in forehand. So the one that is facilitating can do the different, you can do the groupings, you can put things, information in that, and then you can work with it. And what you see here is the result that we had. So a lot of different notes with information, good information from everybody in the meeting. And then we can do the analysis of, what are the main lines in the results here that we can use as well. So that's very good. So I can highly recommend that. And then, of course, as we've been using today, because we want you to participate, but we cannot group you in different things and discuss a lot. So we thought, why not we use the Menti? That's a very good tool as well. And we have been using that before, also here in the agenda work. So we have some really good questions for you, we think. And we will try to challenge you a bit as well and see what you're thinking about different things. So now over to some really hot new results from Adam. So please.
Thank you, Ursula. And I would also like to complement this picture and say that we've also done a lot of desktop research, as it's called, when we have looked at previous agendas and other written information, things that are already online. So we don't start from scratch. We do have some background as well. So what have we found specifically about power electronics? I mean, this is the topic for today. One obvious early finding is that designers of power electronics are in high demand. Vidar, you are one of the persons we have interviewed for this. You told me a little bit, but other people have also reinforced this message, that it's absolutely impossible to recruit power electronic designers today, and it's also absolutely impossible to keep them employed because they are always in high demand from someone else. Excuse me. So these designers, they get offerings from a lot of different companies, which of course is good for the power electronics designers, but it might not be that good for Sweden as a whole. There are the obvious reasons that we all know for this, and we know that the electrification of the vehicle industry is one big factor. We know that we have a lot of battery companies growing in Sweden and employing a lot of people, not least power electronics designers. We also have a pretty good research community in Sweden that is also really interested in recruiting students for doctoral theses and for future research work. So recruiting a power electronics designer today is virtually impossible. Or do you agree with me, Bosse? Yeah, thank you. The second interesting finding is that power semiconductors sort of ticks every box in the vertical supply chain. Power electronics, we have research, we have semiconductor companies, we have buyers of semiconductors, not necessarily the specific semiconductors that are manufactured here, but still. We have almost an entire vertical ecosystem in Sweden when it comes to power electronics and power semiconductors. And that is pretty unique in the electronics sector. I mean, in other parts of the electronics world, Sweden is, or the Swedish stakeholders, they are much more diverse, globally diverse. I mean, they have to interact with people from all over the place. Nothing wrong with that, but there are very few other sectors in the electronics industry where you can tick all these boxes in a vertical, on the vertical line. And the power semiconductor sticks out here. I don't know if anyone else, if you agree with this, or is there any part of this vertical supply chain that is missing today? Yeah, we don't have. There are certain things we don't have. Of course, we don't have semiconductor encapsulation. That's an industry that we don't have it hardly in Europe at all, even though for some very specialized issues, specialized challenges, there is some industrial activity there as well. And there are also some other parts that we don't have. But this vertical integration or vertical supply chain is pretty unique. And the third interesting finding is this, I shouldn't say fight or war. It's at least two technologies that are coexisting, silicon carbide or gallium nitride. If Sweden should pool all its efforts into one big new project, what technology should that be focused on? We have asked this question to some people, and some people say, yeah, of course, it should be silicon carbide. It's the best. And other people say, no, silicon carbide is old stuff. I mean, look at the researchers; they're all in their 60s. And then it has to be gallium nitride or something even more futuristic. And of course, I don't know the answer. We don't know the answer, but we know that it's very difficult. When it comes down to the details, when it comes down to what should Sweden actually put their resources in, it's not easy to find a unanimous answer and say, this is where we should go. Do you agree? Anyone have another different opinion? This is a good opportunity for you to have a different opinion, or at least reinforce my opinion. Sorry? The industry is too slow to adopt. The industry wants silicon because silicon is cheap and abundant. Yeah, true. But so how should we change that? Yes.
We should not polarize. We need, of course, both. We need also silicon understanding. So I think there is no battle between this technology or that technology. The education is the same for all of these technologies, which is a very important supply chain. And who is sort of investing in these all different techniques? That's companies.
Yep.
We can have governmental money to provide or seed things, but it's the industry itself that decides, I want to go with the higher voltages, silicon carbide, I want to go with RF, gallium nitride, and the best solution in between needs to be set by the market.
But if you, as the Swedish government, would invest in one factory for one technology, which one would you invest in? You can't have both. I mean, it's very difficult to have factory or manufacturing capacity that produces both or all three technologies. You can definitely do it on the academic level because you don't. Okay, well, yeah, your view is that the government should invest in education, of course, which is in research.
Also provide other settings for it, but not invest in the infrastructure to have production.
Okay.
It must be private investment. Otherwise, it doesn't fly.
Yeah, but the government can co-invest and support, and if they get two offerings, they have to choose one of them because their budget is limited.
Look at Germany.
Yeah. Yes.
What is the requirement then from the big company? Well, we like 10 billion euros or dollars to be able to set it up. But the question comes from the company.
Indeed. I agree. I agree with you. Yeah. Okay.
Say the things again because otherwise they won't hear.
Okay. So
repeat.
I had a
Sorry.
Maybe you hear. Yeah,
Yes.
yeah. I think the question is wrong. Listen to the discussion about energy in Sweden today. Don't put all our eggs in one basket. So why do you try to get an answer on should it be that or that? I don't like the question.
Okay, thank you. I appreciate your comment. Thank you very much. Let's move on to the next finding. And this is sort of along the same lines, because the stakeholders, you in this room and other people we have talked to, can't seem to agree what the Swedish power electronic ecosystem really needs. Some people say we need more people. Yeah, true, we need more educated people. That I think most people can agree with. Others say we need more government investment to set up more fabs or more factories. And other people say no, we don't. That should be private money. We shouldn't meddle with the industry that's. But at the same time, as soon as something is proposed, this community at large says, yeah, that's all fine and good, but we also have to invest in this. So speaking with one voice is not really is not really easy. Yes, please.
What are the requirements?
Requirements for what? Sorry.
Do you know them?
I mean, requirements for what? Sorry.
If you don't know the requirements, then you end up asking questions. If you know what you want.
Yeah, but I mean, if you but I mean, it's this ecosystem, it's this community that should give the requirements and.
But that's often the question. You should know, or those who decide should know what they're after.
Yeah, but they need. Yeah, but they need help in formulating the requirements. They need help because they don't understand those the powers the powers that are. They understand that there are a lot of opportunities here, but they also understand that it's very disparate views of what is actually required. So I don't agree with you that they should know the requirements. They need help in formulating the requirements.
I've been in politics before.
Yeah.
And I know they know nothing.
Yeah. Okay. You have a microphone here, if you would. Okay. Yeah, but they need help.
They need help.
Yeah.
They need help from you.
Yes, please. Why do we have the question of why we need a factory? Yeah, I mean, we could buy the stuff from someone else. Let someone else manufacture everything we need, and we just buy them.
I want to answer that question.
Okay.
I think that this is a great forum to coin the expression misallocation of talent. We need the factories so that we find talent like Elon Musk to think of the manufacturing processes. Because it doesn't matter that could you all come with a power electronic that saves energy to the production, transportation and utilization of energy, if in order to make those many pieces that you need consume more energy, because the mass manufacturing, mass production is going to consume energy.
Yeah.
So if one more thing I want to say, if you take Elon Musk as an example, what he did, other than put fire under the car manufacturing electrification industry, he perfected the manufacturing process. Tesla has the highest margin in the production line because he's using fewer. He put his mind how he can make the mass production manufacturing better. So, back to the original, we misallocated talent. I think that are talented, and I'm not talking about skilled, talented people that have to think of manufacturing as an industry, as a process, to make that one more, to use the AI, machine learning, because if you look, and you can Google, semiconductor manufacturing, and you see all this production like that, the machines cost the same, be it in Europe or in Taiwan, and there are so little people working there.
Yeah.
But the one that produced those manufacturing like that is not a normal one. It's a talented person. So Elon Musk went from IT world because he could, he got rich.
Yeah.
So he created his own. NASA wouldn't hire him 20 years ago. The best NASA engineer wouldn't work for him 20 years ago. So here we are. I think that we should change the subject to the misallocation of talent. I know people very smart, PhD in nanoparticle, that work in the hedge fund in New York.
Yeah, that's a shame. But there's also, I mean, Elon Musk has done a lot of things that we shouldn't talk about here. So let's not do that. Mikael.
Another answer is that, of course, we don't need to have a factory in Sweden, but it's a good business opportunity. There will be tons of needs to have these power devices fabricated. Why don't we take the chance in Sweden to really have a profitable business, create an ecosystem for the whole electronic industry? Because if we don't have a talent pool, there will be nothing.
Of course. Yeah, I agree.
Adam, now you have a very...
we have to round this up.
It would be interesting to hear your brief summary of these comments.
I think we have to go on. Anyway, the early conclusion here in the there will be a chapter on power electronics in the agenda. It will definitely say that power electronics has never been hotter in Sweden. We have today fascinating opportunities because due to the demands and due to all the reasons that we know. And we need this strategy to harness this strength, and we will do our best to take in all your opinions to come up with that strategy. So I think that is my last slide. Thank you very much.
Thank you. Okay, so now it's time for the.
Now we go Menti.
Now
Do you hear me?
Yeah, nice. So you're awake, I could hear. Oh my God, you're talking a lot. That's great. But we were thinking, let's do this also. Let's do it like this. So now you need to be a bit active. We give you maybe 5 minutes to go in. So you take your smartphone or your computer. You either go into menti.com and use the code that you see there, or you just take the QR code. And then you get to impact the Swedish electronic industry's agenda 2.0. And let's have a discussion then about the results a little bit also. Ska vi I can be.
Ta fram lite stolar, eller
Ja,
ska
det
vi
kan
bara
vi.
ta fram...
Vi kan göra det under tiden här. Ni får säga till om det är några trubbel, om ni behöver någon assistans. Ska vi se. Ska vi köra lite stolar? Blir det bra? Heta stolen. Ja, 3 tror jag räckte.
Ja, vi står.
Yes. Jo, ni får svara.
Måste svara.
Kan du?
So it's basically 2 parts in the questionnaire.
And also, vad har vi?
And it's...
jag ser inte honom. Där. Yes.
The first part is then focusing on the general amount of information that would be in the agenda. And then the second part is more focused questions towards power electronics also, since we are here today.
Does it work for you?
You can see 44 has answered already.
Okay. Yeah,
so that's good.
44 already. So, hur många är vi?
Jag tror ungefär 50.
46.
You're very, very fast in answering, so that's great.
Is it when all the questions are answered?
Don't know. Oh, it actually counts if you have answered also one question.
Good, good. Snyggt gap. Får ta en bättre. Hur går det?
Looks like you're still answering, so we wait a bit.
Just det. Du började med Anna, va? Du... Ja, och så tar du glasen. Hur går det? Ni får titta upp när ni är klara så vet vi lite så när ni är med. Ja.
Back. Great. Okay.
Now
Are you ready for the results?
Let's see. Okay.
Åh nej, säg att den här funkar nu. Så.
Okay.
There we go. Oh, but this is interesting. Now, we have prepared some questions, but I almost feel like to ask about something else now. But okay.
Yeah.
But let's start then if we look at competence on LCA, life cycle assessment for electronic, is too low. And here we see then that it's more towards strongly agree. Anna, why do you think this is like this?
I think that is a part of the overall competence issue we have in Sweden. We need engineers in a lot of areas, and I think this is an answer of that question. Not also. So more collaboration regarding competence overall, upskill, reskill, and collaboration between companies and universities in order to educate what companies need.
Great.
I stop there.
Yeah, thank you, Anna. Do you agree with Anna, or is there something that has another opinion? Why is the knowledge about LCA so low within electronics industry?
Because they are not given the opportunity to learn.
The one answer was they are not giving the opportunity to learn.
We need to take the microphone like this.
Do we have one more microphone? We can run. Okay, you can share there.
I think, as was said, the whole understanding of life cycle assessment is low in all sectors because it's not defined completely what should be accounted for. There is some programs in EU now looking into sustainable electronics. And they admit themselves, the program chairs of that it's not completely defined what is what. So there is a lot of activities to understand what is the sort of load of producing semiconductors, but what is the benefit? If you cost something to produce them, but you minimize the waste or the pollution by a factor of 1,000. How do you assess that? So I think it's a matter of definition. So surely we should have a better understanding of life cycle assessment.
Good. You wanted to add?
Please add.
Yeah, I wanted to ask, oh my God, I was on the next question. Would you pay more if it's made in Sweden? This is such a false sign. assessment of the problem, because the equipment is the same. And again, if you put more people, more smart, talented, motivated people with, to work on the manufacturing and mass production, nothing says that Sweden doesn't come with an idea to reduce the price of the manufacturing. So it must not necessarily is going to be more expensive to do in Sweden. And one more thing when it comes to why we should have factories in Sweden, because in order to be a robust country, you need to have skilled labor. And if you don't have factories and everybody's working in IT and advertising and whatever the digital economy developed skills, Elon Musk included to begin, we don't have this readiness if a crisis occurs. So we need skilled labor.
Mm-hmm. Yes.
Okay, the first one, the competence on life cycle assessment for electronics is too low. I think I agree, but this should be rather more, not 6.7, maybe 8.7, something like that.
So
why?
even higher.
Yes, why I am saying.
Okay, yeah.
Sweden is, I think, the country where you produce a lot of skilled capital, you have a lot of infrastructure, materials, semiconductor devices, and power electronics.
Yeah.
We don't have neither any group at any university or in any company that do some life cycle assessment, reliability engineering, failure analysis, what's going on. This is one reason. Secondly, well, you can compare with Denmark. They have the best, for example, the reliability group, Aalborg University. You have some groups in England. You have a lot of groups in Germany. They produce power electronics or electronics. They do reliability assessment. We don't do here in Sweden at all, to the best of my knowledge. Someone could challenge me. Second point. Well, this is one thing.
Don't try, Helena. Yeah. Please.
Okay, but
what a lovely
Please
audience.
go on. No, please go on. I meant that.
Yeah, no.
No, I meant that.
Go
I'm
ahead.
just joking, so it's fine.
Second point is there is no unified LCA, so it's more specific, application specific LCA. Different application demand different set of LCA. So this question is rather be more discretized in specific application, low power, automotive, traction, high power electronics. So there are no unified life cycle assessment in place.
Yeah. Okay,
Great.
just a comment also on the, you mentioned the question number 2 here about the price. Because now when we have also been doing all the interviews, we put that question, if the price is really a part of the decision. And some answers that no, we cannot buy if it's, we need to have it as cheap as possible, and some are saying the opposite, that they can do that absolutely to be secure that there are materials and components and what you need for your factory here in Sweden or for your production. So it is, it's both ends, I would say, just to comment on that question.
Yeah, so these are 6 questions out of a full agenda, and it's a little bit for you to think in the boundaries, but of course this is included in this type of discussions, and this is what we discuss in the deep interviews also.
Okay, you wanted to make a comment here? Yes? Wait. Yes, the microphone. You can be loud.
Thank you. When you mean I could pay, does it mean you as a consumer or you as your professional job?
Professional, it was meant, yes.
Then I think it's maybe a different answer.
Yeah, could be, yes. Okay, I think we go...
on that too. If
okay.
the answer would be strongly yes,
yes,
then we should put the factory in China or US, because then it's much more people that would pay for it.
Okay, that's also a thought, yes. Okay, I would like to go to the next one, which is also quite high, an 8 on the, to enhance the Swedish electronics industry, we need to collaborate more in the value chains. So I would like to ask Ganesh about that question. So what do you think about that?
Yeah, we're so alike, so we...
Yeah, you are alike, yeah, just, yeah.
You know. To distinguish us. Collaborate in the value chains, I mean, between different stages in the value chains?
Yes.
Well, I think we do, to some extent. I think it's probably more interesting to look at collaborating across value chains. I mean, from different...
Okay.
In the sense that, let's say, you have the same... of course, at some stages, it's the same value chain, but let's say between the applications for the same type of components and so on. I think that's where you'll get some crossover effects.
What do you think could be the benefits if we can do the more collaboration?
Well, yeah, obviously you will learn from each other's experience. And in some cases, and I just talked about that yesterday at the wide bandgap seminar, there is a convergence. I'm from the rail industry, and we see from the road industry getting electrified. We will not use the same exact devices. We will not use them in on the same missions, etc. But there will be a lot of similarities there. And from that perspective, there is a lot to be gained from sharing experiences and actually finding best practices, etc. So that's what I think we can get, yeah.
So what do you say? So some other aspects than Ganesh was mentioning, yeah? Yeah, I bring this here. Oh, please.
Maybe too many comments, but anyway, I think it depends on how we see about the collaboration. I think we absolutely need that, but we have to have respect for each other's field. So I see the tendency now that, okay, we need designers. Designers, they just design. But to be a good designer, you must understand why is this design set like it is. And then you have to understand the technology behind it, to understand also the whole flow, especially when we discuss the life cycle assessment. I think we need to have a much broader understanding of the field, and that is in a way a collaboration and respect for the different levels of integration. So we need to have a broader look at that.
Okay. Good, thank you so much. So some more comment on the value chains? Before, yes, you may, absolutely. Please.
I agree with you that there is a cooperation in the everyday life, but also it was academically researched, the cluster effect. When you put different industries together, some new industries or solutions appear. And it's, one example is like Alzheimer's and dementia and game, PC game. Very strange example. So it's good to put things together.
Yeah. Thank you so much. Okay, Helena?
Okay, should we place a question to Claes also here then? Let's take let's take the next one actually. We have a 7.2 here in the if we should fund more startups within electronics, but what do we need to focus on then for that funding?
I don't know. No, but I think it's an interesting question, and I think I posed yesterday we had a meeting on wide bandgap electronics, or wide bandgap power center had a meeting, and I posed a question: has Sweden been in the forefront of wide bandgap development? And a lot of people raised their hands. And then I asked the question, is Sweden still in the forefront of wide bandgap development? And then almost no one raised their hands. And then I asked why. And then one of the answers was that funding for research and also startups and getting the motor running. The motor had been running for a long time with silicon carbide and gallium nitride. So the funding kind of disappeared. And that is why a reason we are not in the forefront anymore. So I strongly agree with that question that we should fund. I just don't know what. That has to come from well, maybe researchers, but industry.
Can I comment too? I think we need a long-term strategy from the government where you have goals and also funding connected to those goals, because otherwise it will be very scattered. So long-term strategy, because then it will be, you will see, okay, we're heading towards this, and it's easy for industry and startups and so on to also to see what is the government funding for.
So government should make a long-term strategy and secure funding, and then but it has to be business driven. Yeah, that's my thinking as well.
Well, I kind of disagree in some aspects here. I mean, I basically live in the wide bandgap semiconductor startup industry right now, and there's many very, very good invention coming up in companies from Kista and Linköping, Lund, Chalmers, and also one of the best initiatives from Vinnova that I've seen in many years. I was on the board of a Zenit program in Linköping, where we had like, I think, 14 or 50 participants, startup companies, Ericsson, Saab, Hitachi, and developing gallium nitride, hemp structures, very, very unique. I think basically people all over the world looking at those devices right now. Epiluvac, company I was part of myself, did a very, very nice development of next generations of equipment for silicon carbide. And we have a fantastic company here, Kista, in Kista, developing next generation of dislocation-free silicon carbide wafers, which is what all industries all over the world is waiting for. So we have tremendous opportunities to continue to develop cutting-edge technology here.
Since we have this flow of microphone,
yeah.
I'll take the chance.
It's on its own way.
And I agree with Bo, of course. We have been together for quite some time. And I think also the lack of people today, there is no lack of startup funding. Easy piece to do it. But what is the next step to grow the company from 10 people to 100 people? That's the question, not the startup, but to nurture this the organic growth of the company. It takes time. And sometimes the external investors are too early to show up the big money and we sell. And the reason why we have lost so many people that we have actually educated in Sweden, most of them are gone to rest of Europe, to Asia, to US. No, and if we don't have the talent here, nothing will be created. I said it before, but the only, there is not just money from this government that attracts other companies coming here, it's the talent. So we need to have a fabrication facility here to even be able to keep the people. That's so important. So the startup, I think the question is not completely relevant. Startup is no problem.
There is a type of startup which is very creative and revolutionizing in the laboratories, in the startup that you're talking about. They are incremental progress. The government we should learn from history how the digital era revolution happened with products that were not thought to the end purpose that they ended up to serve, like computers. They started, unfortunately, during the wars and during the Cold War, which wasn't a real war, but that gave us the computer and the internet. So we need a government to step in and to prepare us for crisis or to prevent crisis. And there, probably, the government used to make it in the corporate laboratory. Bell Labs was one of them. They don't exist today because they dissecate. Today is something called public-private partnerships. It's another way of creating this environment to come with revolutionizing technologies, not that making a better process and a better thing. We need factories.
Good.
You get your point.
The message is clear. And now
we have another one. Yeah.
So, please.
I think you, Mikael, you stated this when we started up this with the challenge of saving 1%. I've been working quite a lot when I was part of the board for the Swedish electronic industry. I've been talking a lot to authorities, and my experience is not very good. We have this EUP directive on energy saving, you probably know about. Abandon some products, but I have met high people from authorities saying, well, now we have set the directive or the law. Now it's up to the industry to fix it, and that that attitude has been very provocative.
Yep. Thanks. Thank you for that.
Okay, I think we need to go to the next section. Just to a note, really high then on the people that need to learn more about design of electronics. And you were on this before as well.
Yeah,
so yeah.
And now we have some other questions here.
Yes.
Yes. The
Let's
final
go
ones.
to these ones that we have never seen them before.
No. So, do you want to? I'm just doing like this. Yeah. So here we had about that the Swedish government should co-fund manufacturing of power semiconductors. That was scale free. But how much was the fully was 5 or?
Co-found, co-own.
No, not co-own. Yeah. Okay. Co-found. Yeah, but is 5 the highest? Yes. Yeah, it was 5. Yeah. Yeah, different scales. Okay, yeah, no problem. Yeah. So, and then we have 8 to 10 years, we have all the power electronics engineers we need. Not so high agreement on that. And EU Chips Act is a great opportunity for Swedish power electronics. Yeah, a bit higher. And then also says should publish a guide on power electronics. Yeah, also quite positive, yes. So now we were thinking of to hear, Anna, could you please, yes, okay, could you please, yeah, you pick your, what question here is really challenging you, or what is giving input?
I think I would like to pick the EU Chips Act, if it's a great opportunity for Swedish power electronics. I think that depends on how the Swedish government plan to act regarding if they are going to co-finance. I mean, Vinnova told us this morning that the co-financing from the government was quite scarce. And they not so much money appointed to it, if not the industry does something there. So I think that is the main conclusion. If the government appoints more money for making it possible to apply EU funding, then it might be a good opportunity. If the government says no, then well, it will be hard for Sweden to be a part of.
Yeah. So then I would come to the next question to you. Then is, how should they know that they should? How should they know how they should think? The politicians.
Well, we need to help them.
Yes.
Absolutely.
Yes.
Tell them where are we strong in Sweden today? Why should we allocate money on this? And why is it important for the Swedish industry as a whole, not just electronics, but Sweden as a whole, because SJIP's joint undertaking is more than just electronics. It's
Absolutely.
So we need to point out the importance of it.
Yes. Okay. So, Ganesh, what do you think about these? Something here that is that you want to comment on that is really.
Well, maybe I'll pick another question than you did. Yeah, sorry, I'll take another question. In 8 to 10 years, we'll have all the power electronic engineers we need. Yeah, I think that's maybe even lower probability than what's said there as the average. And I would say that's just simply because those people are, what, 15 years old now, right? And are they planning careers in engineering? Some of them, hopefully, but probably a majority not. So I think we've already lost that race. So the question is, what do we do with those who are maybe 5 years younger? And that's probably where we can make the difference. However, what we could do is also that we're talking about reskilling, right, in industries which are transforming. So that's probably where we could look to get the necessary talent in this area.
Would it be possible for your company to collaborate more with like preschool, daycare centers, first and second grade? Would that be possible?
Yeah, it could be. I mean, I think it's not just. I think the problem is that when it comes to that particular area, I think it's that we all see the need, but we do kind of piecemeal, haphazard initiatives, right? Which are good individually, but they don't necessarily contribute to the whole. So I think that's one thing. But I think there is a point in that, because I'll just give you a short anecdote. Yeah. When my daughter was in preschool, one of her best friends and her there at preschool were playing with small model trains. And so they came into a discussion later on, like, so what does your father do? She asked my daughter, and said, oh, he works with trains. And the eyes of that girl just popped out. What, he gets to do this every day for a living and gets paid for it? So yes, I think there is something to do with that, to get the context as an interesting and attractive area.
Yeah. And I agree with you. I mean, now I'm part of the discussion, I feel. But I agree with you that we should be much early on than when you are 15. That's too late. When you are preparing for like third stage in public school, I think that's the probably where we should be before you do the choice. For the future. Sorry.
I think maybe perhaps. Yeah. I maybe just add that I think there is some evidence actually. I believe that like when children are around 10 years or so, that's sort of when they're most susceptible or easy to reach and attract. And that's probably where you need to. But it needs to be like a consistent. You need to be able to see that later on, that there is a future in this business and that it's attractive and that you're actually contributing, for some people at least, that you're contributing to something greater than yourself and just a pure career, right? And so I think that needs to be reinforced. And it needs to be done jointly, not necessarily as a national plan, but at least a national initiative with several stakeholders collaborating. Yeah. I think we have
we have a question there, but then I think, Claes, you can prepare yourself for commenting one or two of them. Yeah, soon. I get some exercise here in the stairs, so that's good.
Yes, I have a question perhaps to everyone here, because I was in this meeting 1 year ago in Västerås, presenting, but also taking part in the discussion afterward. And I learned that, in principle, you can't study electrical engineering before university. And you mentioned just 1 minute ago, at 15 it's too late. My understanding is that in a gymnasiet, the gymnasium, when you're roughly 15, 16, you can't select electric engineering. There is societal design and the mechanics and, or I don't know the right words here. But is there someone who can comment on this? If something happened the last year, if it's now possible to study electrical engineering in the gymnasium?
Feel free
Question
to answer. Yes, absolutely.
Because
answer.
it's not good as it is.
No.
I can comment, since my son is starting high school this fall, and I visited 6 out of 50 high schools in Stockholm only.
Excuse me?
There are about 25 that offer technical program. I only found one that had a course in electronics. They teach technology, technique. There hasn't been electrical engineering since the 4-year technical program that they killed many years ago. And that's never going to come back either. And the reason, there are no teachers. They hardly have teachers who know programming in high school in Sweden. And try to find someone who knows Ohm's law, Kirchhoff's law. Nope. Sorry, because they're all working in industry at Ericsson for twice the salary or more. And that's part of the answer.
What team is that? Ohm's lag. Okay, sorry.
Yeah, and in the technology courses, it's a lot of bridges, learning how to build bridges and different kind of bridges and so on. So it's, well, we lack some teachers, I would say. I agree with you, Pelman.
Let's see now. Yes, yeah, there, please, first. Yeah.
One more question here relevant to the, in 8 to 10 years, we will have all the power electronics engineers we need. I think we should focus more on gender equality in power electronics, because here is the big gap.
Absolutely, yes. What do you think that we should do?
We should try to find a way how to improve the gender equality.
Mm-hmm.
This is the more fundamental, because it's mostly the male-dominated male-dominated area.
I agree with you, but I was thinking of the action list. What is it to do? I mean, what do you think we should do? Do you have a thought of what one of the solutions
can be? The next question, how to do this? So we should find a way how to improve this.
Yeah.
That's maybe another debate we need.
Okay. I think we.
Yes. There also first.
We have there, please. Yeah, hand it over.
My experience is there's also a difference between the power electronics industry and other electronic industries on the expectations, on the experience from the people applying for jobs and consultant business as well. I don't know why that is. Maybe it's because power electronics is considered a difficult field of work. What are your comments on that?
Yes, yeah, please.
So the question was, or what you said was, if I understood it correctly, that because of power electronics being perceived as a difficult subject, you don't get people applying for those jobs, or did I? Okay. So the industry expects too much from people. Yeah, I mean, obviously, if as an industry, it would be great to have freshly graduated students with 10 years of experience, but that's not going to happen. So we understand. But I would say, actually, I would probably be a bit contrarian to that, and I would say that I think what we need is a lot more engineers, full stop. And then once you start working, that's where you get the domain expertise. So I'm not too worried about that. It's more than to get the interest of potential job applicants to seek this particular industry and so on. So general engineering, and then of course, yes, electrical engineering and so forth. But I don't think we necessarily need to have. I have a lot of colleagues who were like engineering physics majors, right? And who are excellent power electronic engineers. A lot better than me, who studied it. So.
Okay. Yes. Yeah.
Is it on?
Yep.
Yeah. On the many different things we have to do. The gender equality is, of course, a even bigger challenge in the power electronics. So there we have this narrative that it is a sustainable technology and very versatile what you do. You just don't design the interior of a semiconductor, but you are doing things for the whole system to really minimize the carbon dioxide footprint and so on. So we have to have a joint understanding how we speak about this, and the companies, I think, should take even a more active role in working together with the universities. If we take that part, the high school or gymnasium is also the same need, but what we can do at KTH, Chalmers and so on is basically to work much more integrated with the companies. So we have students coming in directly from the gymnasium, and then they are pretty flexible. They start in one program, but since we have now a candidate program and a master program, there are big greater flexibility than it used to be. So I think we can change the mindset if people see role models from industry, and not just one person from Alstom, yourself, coming in. That's great. And we can see this variety of different stadiums. We have the reskilling, people from industry, your own industry, but also the very first fresh students coming into university. That's a completely different scheme. And we can do that because we have that in Sweden, the possibility, if we collaborate. So that we not say it's the company's responsibility or the university's responsibility. We have to do it together in a completely more integrated way. That's my view.
Thank you.
Maybe just if I might just comment on. I think you're onto something there. I'll just give you an example from like when I started. I mean, when I studied at KTH, you were required to have summer jobs or internships, right, for 12 weeks or something like that over the course of your studies in order to get the degree. And that, I think, has been abolished for a number of years. But I think that's a good way of where you see actually what's being done. And that's actually one of the summer jobs I had was at the company where I'm with now, right? So and I could see what you could do, and that's probably the only way, really, because otherwise it's just my kids think I just do emails and PowerPoints, which is probably true, but.
Okay. And that was also connecting to my question, because when I looked at the university, to go to the university, I chose based on that they had a trainee period of 1 year, and that was, you need to really find that education in Sweden. It was, and then they completely took it away after that, actually. So should we take that back? Why was it taken away?
Yeah.
That could be a good,
yeah. I think also we perhaps should put more emphasis. Now I don't remember exactly who also brought up how much less footprint are we working with and so on. But the purpose beyond what we are doing, I mean, why are we doing, what is the work really leading to? I think that is a really big question that we need to communicate a lot. I mean, both of course, one cannot always just look on one's own children, of course. But when I talk much with their friends and so on, they won't employ in a company where they are not, where it's not in line with their values. So I would say if they come to your company and think, oh my God, this looks so unfashioned, and they don't know what an LCA is, and they don't care about then perhaps they are not interested. So I think to be an attractive working place, we need to shape up a bit and really think about why am I here? What is it that is so good with this company? What are the real benefits from this? And what are we contributing with? And not just thinking, oh, it's so interesting with power electronics in itself. I like that a lot. That's a really cool thing. Yeah, for some it is, but some people want the bigger, objectives to be able to evaluate where they want to go. So I think that you will capture both women and you will capture other men than you are capturing right now. So I think that's a plus.
I think that's an interesting point, because I think if you just look at what used to be called data science and rather dull subject for 20 odd years ago is AI now, and then suddenly everybody wants to be in it.
Yeah.
But it's still the same math and stuff you have to do, right? And so people are apparently willing to put in the effort to learn those things. So I think it's the context again, as you say, that sort of frames the interest.
Yeah.
Yeah.
Okay, now we really quickly we let the class take last.
Yeah, so I'd like to start by commenting on that same question and then move on to another really quickly. My take on the 8 to 10 years question is that it's a great result that we have low score here, because one, it puts it on the map, and two, power electronics will be really, really needed also in the long-term future. So we will have a long-term need of power electronics, and that seems to be the consensus here. And that is good, I think. So that is leading me to question number one. The Swedish government should co-fund manufacturing of power semiconductors. That's a very long-term proposition. So if we know that we will have a long-term need of power electronics, and we also need talent, as we said, I would say why not? But I would pose a counter question: if they don't, who will fund it? Will there be a manufacturing of let's say pilot line or increased pilot line or maybe production of semiconductors in Sweden on a higher scale than exists today? That's my counter question.
Okay, François. Okay, and just checking with the boss.
Well, short thing, yeah. Well, I think actually the government do a very good job right now with Vinnova. I mean, they help us to kickstart companies, and they kind of co-found us because they have fund Electrum laboratories and other laboratories where we can work for really cheap money rather than to buy all the equipment. I've been in a few startups in the US where you had to raise maybe $15 million to get started, and here you can raise, well, 5 million Swedish crowns is enough to get started, actually. So that's my take on it.
There are great possibilities. So what do you say, Helena?
Yeah, now we're taking coffee time.
And then we end.
I think
one for the coffee, and then we end.
I think maybe the word co-funding is misleading. I think it's a sort of co-funding, but if we have an attractive manufacturer wanting to set up something in Sweden, they want subsidies to do that. And of course you can call that a co-funding, but co-funding is more sort of integrated with ownership and so on. And there will be nothing if we don't have that subsidies coming. So I think maybe you can think about maybe rephrasing the word, because the Swedish government is not investing in companies. They invest in getting jobs here.
Good. Okay. Now, as my son usually says, just one more question.
Right.
You know,
it's like Columbo.
now
But
the last
actually,
one.
there was the lady up there, I think in pink. You were about to ask a question, I think, right?
Okay.
You wanted to ask. I think you raised your hand. Did you?
Did we miss
No?
somebody?
Did we miss somebody?
That had a question? That
No,
was
no.
earlier.
I think you in pink there. I'm not sure. I thought you raised a hand. Okay, sorry.
Sorry.
I just thought we.
Yeah, well, you missed. Okay, thank you so much for your concern. So now, please.
Thank you very much. And now it's fika time again. So you will have coffee and something sweet to eat outside. And I will urge you again to discuss with each other and continue the interesting talks you have had. Thank you. So now we're back from the Swedish fika. We have a small change in our program. We have switched places on two of our companies that are here today. So here we have Heart Aerospace and Johan Helsing. Welcome, and I give the word to you.
Thank you. Thank you for inviting me to speak here, and sorry for messing up the agenda, but I have to be leaving before 4 o'clock, and we have the presentation up there. Hi there, I'm Johan Helsing. I have been working in the automotive industry for 25 years, and 2 months ago I made a shift to the aerospace industry, so I still need a little bit of notes here to cope with it. I'm now working at Heart Aerospace, a company that is developing an electric airplane, and I'm here to give you this short introduction to our company and our vision mainly, and of course speak a little bit also about our need for and interest in power electronics. Air travel is something we today take for granted, but quite a remarkable thing actually. One of the genius inventions of our time, allowing us to comfortably get anywhere on the planet in less than 1 day. Being connected to this infrastructure is as important as being connected to the internet, which is why it's so painful to acknowledge that it has such damaging effects on our planet. And as air travel has grown during the last decades, so has also its emissions. This came to an abrupt but short stop in the lockdown, but emissions are now back to where they were before the pandemic. But it doesn't stop there. Globally, air travel is only in its infancy. Only 20% of the world's population has ever flown on an airplane. So by 2050, the emissions from aviation is expected to triple, going from maybe 1 gigaton today to close to 3 gigatons. And we have to break this trend. We know this. We need the new technology, and we need a new generation of aircrafts that can completely decarbonize air travel. So we ask ourselves, how do we kickstart this transition? Our focus, yes, our focus is on short-haul flights, which constitutes 1/3 of emissions from aviation. So this is where we start. Short roads first. And we unlock this transition by focusing on the product, on the market, and the industrialization. And going from left, make something new. Having 0 emissions by 2050 means we have to start now. As an aircraft lifetime is about 20 years, we start fast by using existing technologies where possible and innovate where needed. And we also want to make something that the airlines want now. We have an advisory board with members of airlines, of airports, and airplane-owning companies, and they support us in getting the right value proposition for the market. And future-proof, it's building a platform for a family of aircrafts. It will become cheaper to operate and to produce over time, and it will be prepared for future technical developments. At Heart Aerospace, we developed the ES-30. It's an electrical airplane designed to transform regional air travel in every part of the world. The ES-30 seats 30 passengers in a 2+1 seating with a comfortable 30-inch pitch. It has a fully pressurized cabin, it has standing height in the aisle, and it has overhead bins. It has a luggage compartment in the back, allowing each passenger to bring 25 kilos of luggage. And it also has the option of a galley in the front, which means it's possible to also add a toilet in this relatively small aircraft. The technology in the ES30 is unlike than any other real aircraft. It brings a real level of comfort and capability that we normally see only in larger airplanes, which allows the ES30 to operate in every weather, including low visibility. It can even fly in every climate. The ES30 features a state-of-the-art electro-expulsive de-icing system so that we can fly into known icing. The technology is purely electric. It's low energy and durable and scalable, and ES30 will be the first passenger aircraft to apply this new de-icing technology on the wings. Now a little bit look into the propulsion technology. The ES30 is an electric airplane driven by electric motors powered by batteries, which allows it to operate with zero emission and low noise. The batteries, which are placed in the belly of the aircraft, provides power to the 4 electric propulsion units. And the aircraft actually includes also a reserve hybrid configuration consisting of 2 turbogenerators powered by sustainable aviation fuel. The reserve hybrid is installed to secure reserve fuel requirements without cannibalizing battery range. This means that to be allowed to start a flight, you have to have energy capacity for something similar to that flight. And this reserve hybrid, it means that we can utilize the batteries, so to say, for the original flight and have this as spares. We have designed the ES30 to have a 200-kilometer all-electric range and enter into service without turning on the turbogenerator. And it's really important for the market, for the route flexibility, and for the long-term planning of the airlines that they can fly further in case they need it. So for this flexibility, we kick in the turbogenerator in case we need to fly further. I was reading faster than text, yeah. So that was the 200-kilometer all-electric range. So with the reserve hybrid, we can run 400 kilometers with fully load and still reduce emissions by 50%. I would like to leave you with an insight here. We keep the focus on the short routes, but we have spoken to a lot of airlines, and the main challenge of flying small airplanes is not that we cannot fly far enough, but to have the right unit economy. And by being electric, the ES30 can operate on good unit economics, better than the competition. And as we know, price of carbon will increase and price of batteries will decrease, so the economic propositions will be even greater. Now a little bit about the power electronics. As I said, it's the heart of our aircraft. It's clearly central in electric aviations. Operators will expect high efficiency. The flight safety agencies who approve this design will of course expect highest possible reliability in both the hardware and the software. And EMC and EMI aspects are really important still. And here is just a short summary of what you can expect of the power we need. Bear in mind here that the conversion capability, which I write to the left here for the DC-DC converters, that are the conversion capability and not necessarily the power consumption, because of the requirements for redundancy, there will be needed, the installed capacity will be a bit more. But you can see here about 3 megawatts of propulsion power, which we will implement by highly efficient, proprietary designed direct drive synchronous motor units. For the reserve hybrid system, it's about around 2 megawatt conversion capability. And then for charging, we expect to use this MCS standard, which it's not said that this is it's more the capacity from the charging system with the 2 steps taken, first 1500 amps and 3000 amps and our 800 volt battery system voltage. It will be about these charging levels, so that's what we need. Being electric, ES30 is unlike any other aircraft. It will be low noise and almost silent taxi. It will emit no local pollution, even when flying using the hybrid system, because that is not used during takeoff or landing. This, together with the short runway operations, means that airports can become more integrated with the communities. So we want to change not only the experience of the plane, but also of the airports. The ES30 is green, it's affordable, and it's accessible, and it will enter into production in 2028. But it doesn't stop here. The ES30 will continuously be upgraded as new battery technologies become available, making it a product that gets better the longer you own it. So that was the end. And sorry for reading from a manuscript. I can't really take it by heart yet, but thank you for listening.
Thank you very much. And what would you say are your biggest challenges in the near future for your company?
Probably funding from to get the money from investors, but maybe it's more fun to talk about the technical challenges.
Yeah, if we focus on the technical challenges.
I'm new to this business, but I realize how big difference is compared to the automotive industry, because here we already from the start need to cooperate with the authorities approving the design. They need to be involved in every detail and approve every step we take. So that is a challenge, because the authorities don't know either what they require from an electric aircraft. So it's fascinating, and we learn together with them.
Okay, thank you very much.
Thank you.
Yeah, we have some time for questions, absolutely.
I was quick.
How do you cool the power electronics and the electric machines? Do you have water cooling, or is it by air?
The question was, how do you cool the system? Is it water cooling or air?
Yeah, I would say it's not air cooling, even if it's good possibility there, but it's water cooling could be a possibility. It's more likely with oil cooling, and both. Yes, and a small remark here, because even if it's 30 minus degrees outside, we expect the airplane at the airport. When it's landed, it has infrastructure, it can charge, and it can keep the temperature of the systems. So we will have a fairly good control compared to the automotive. We don't park the aircraft to soak in minus 30 and then start.
Some more questions? Yes.
One more technical. What is the maximum operating temperature for your semiconductors?
The maximum operating temperature for your semiconductors.
The maximum ambient temperature we have to survive in is plus 55. That's required by the authorities. This will be a challenge. 65 degrees is typically what the suppliers of the inverter systems want, but I think we have to push that a little bit. But it should not be, it's of course compared to which power you need at which case and so. And I think that we have a possibility, as I said it here before, when we are down on the ground, we can condition the temperatures and so. So we'll have to solve it, but hope it was an answer.
Are you going to consider silicon carbide?
I would like to.
Silicon carbide.
Yes.
Was the question.
Didn't you see me writing that implicitly? High efficiency, high reliability. Of course, I want to use silicon carbide, but it has to be, as I said, this in combination with the authorities. They have to kind of approve that we use new technologies.
Thank you very much. And I know you will have to leave for your train in a couple of half an hour or so.
Not for my plane, for my train.
No, for your train.
Yeah.
For your train, not for your plane.
Could have been.
Yeah,
so
could have been.
I wait till the aircrafts are electrified.
Okay.
Then I take the plane again.
Good. Now, ST Microelectronics and Björn Magnusson. Very welcome.
Thank you for inviting me to come here and talk today. I will speak about ST Microelectronics. My name is Björn Magnusson and I work in Norrköping. So maybe just a few short facts about ST and what we do there for the people who don't know us. So this is one of these global semiconductor companies who manufacture semiconductors that you actually use every day. So it's 50,000 employees and revenues are $60 billion last year. So it's a big company. And thinking on where we are, so actually all of you are using ST Microelectronics devices in your different applications that use electronics today, for sure. Even if you don't know it, you and your kids and your family use it every time. We are in automotive, industrial, personal electronics, and also in this cloud that exists somewhere in reality. So just to go to see who we work with as customers, because this is always a good thing to see what are actually there. So ST list the top 10 customers that existing. So of course, the first one is of course Apple, everybody know. Then we have some automotive makers, Bosch, Continental, computer makers and so on, even going down then to SpaceX and Tesla. So these are the biggest customers. So then you recognize that, okay, this is something I have around me. If you now move into silicon carbide. So silicon carbide is today a rather small business compared to the entire semiconductor business. But it's something that grows very rapidly, and therefore it's of course very interesting. If you look inside ST Microelectronics, we had 2021, roughly $500 million of revenue for device sales. Last year, we moved over 700 million, and this year to go to 1 billion. So 1 billion compared to 16 is something, and you see also the growth there is really, really rapid. So this is a key thing. So what drives this whole growth? So roughly today, roughly 80 customers, we have 20 of these are car makers. So all these electric cars that comes to the market now, there's a lot of consideration if to go into silicon carbide or not, but the number of programs are there, and let's see if we can make them successful. 75% of the revenues of device sales in silicon carbide comes from the automotive. You of course have the car itself, but you also have a charging infrastructure around it. So to meet this, I think ST made a really, let's say, decision. So let's vertically integrate. You need to have a device, you need to have a backend with the system, but you also need the material, and the material in silicon carbide is really a lack of material. So that's why we in Norrköping came into the picture 2019 when ST bought Northstar. Of course, automotive means dual sourcing, so both production in Europe, but also in Asia, and so on. And moving to bigger substrates. 150 is today the main substrate used for device production, and now we move into 200 millimeter. And in parallel, of course, the device people work on the next generation of devices. So the supply chain here is, of course, very important. We are over here buying things that contain electronics. And what we say is in the back end, there we have done a package and put it into something that can be used in application. And before that, we had to make a device. And to do have a device, we need some substrates or crystals or materials. So in ST, we call this kind of front end. And then we have backend to put into a package, and then we have application. So how does it look for silicon carbide into ST? So basically, if you look on the front-end side, then we have Norrköping, there we do R&D for substrates and crystals. We have Catania, there we do wafer fab, we do the devices. Singapore, the same. And then you have a backend in Shenzhen and Boscora in Morocco. So this is basically how the material moves around the world before it gets into the device. What is new there is, of course, that Catania, there we not only have a wafer fab, we're also starting up the substrate and epitaxial fab. So let's look just a few slides what we do in Norrköping. So it's really a key thing is development and industrialization. And then I want to kind of just go 20 years back and say my part, how I thought things happened here. So it was a big research program called SciCep by the Strategic Foundation. We had KTH there, Linköping University. We had Documentic on the material side with Linköping and ABB with KTH, plus a lot of other things around it. And what came out of this thing was actually a lot of people with knowledge, a lot of processes, patents, equipment, and also a lot of companies. And both here in Kista, but also in Östergötland, in Linköping. So sometimes now when we talk about the Pillar 1 in European Chip Act, what I see is what I'm really afraid of is that we split everything in so small pieces that we don't really get anything. I think this was a rather unique project because it was big and you had a cluster. And not everybody stayed in Sweden. But we also had got people who came outside Sweden to come here and said, I want to be in this country because here's a really strong activity. And some of these people, they are here today also. So what I would like to do with the Chip Act Pillar 1, can we do something again that is big enough? And to be honest, of course it's nice if it's silicon carbide. But I'm okay also with gallium nitride or gallium oxide or diamond. Because some of these people will come to silicon carbide anyway. It's a question of developing people, teach talent, and so on and so on. And if it's big enough, you get this critical mass to create something. I think this was done at West Point, but we need to do this again. So this is my perspective of Chip Act Pillar 1. It doesn't have to be silicon carbide, but it has to be done. The worst thing is if you don't do anything.
Questions?
Do you have epitaxy on 200 millimeter?
Yes.
For which voltage class?
What we do roughly now is for 1200 volt, most of it. But it's not really in the machine, it's no restriction on that. So.
Yes. Hi, Björn. Thanks
Hi.
for your presentation. So I'm Lars from Vinnova. And unfortunately, you cannot go back in your presentation now, but you had a slide there on projects, European projects that you're involved with. And before you came here in the meeting, we had a discussion about the CHIPS Act and CHIPS joint undertaking. And I think those projects are within the framework of CHIPS joint undertaking, which is now called KDT.
Yeah.
And maybe you can reflect a little bit about the advantages with being a Swedish-based company, because you are in Norrköping, into that type of program like CHIPS joint undertaking that involves quite a number of European players, small companies, large companies within these specific projects like Archimedes. So what is the advantage for ST in Norrköping to participate in CHIPS joint undertaking? Thank you.
I think maybe one very concrete example is our 200 millimeter epitaxial system came to us through one of these projects. So we got the machines very early and we could install it and get support to that. So that's a very concrete example that we actually had a project related to what we really wanted to do. But otherwise also if we see this as a very strong vehicles for testing something new that everybody agree we should do regardless, but never get done without a formal project. And also I think it's helped to get the resources that you wouldn't have inside the group SD, but also connecting to other, let's say, equipment suppliers, but also, let's say, other parts of the supply chain. So I think in Sweden we don't really have any good platform to work together in a more, let's say, organized way. In Europe it's also lacking that except for these European projects. So I think there is what we see the benefit. It's not always that the project itself, exactly what is written in that document, is the most important, but it's also other things that you comes together with it, just because you meet other people, work with our companies.
Thank you very much, Björn.
Thank you.
And our next speaker, please welcome. We have Ronald Vogel. Is it Vogel or Vogel? Vogel. Vogel.
Americans say Vogel.
Okay, Vogel.
Yeah.
And from Coherent.
Yes.
Yes. So please.
Thank you.
For reverse laser pointed and you see.
Okay. Thank you very much for the opportunity to have an American company presenting here today. But it has good reasons. Actually, a lot of our products come from Sweden. Actually here out of this building, Electrum, but also from Järfälla, where we had acquired companies. So I'm filling in here for Christian Fieder, who couldn't make it today. My name is Ronald Vogel. I'm in charge of business development and sales for silicon carbide epitaxial wafers globally. So Coherent probably is not a recognized brand name in the silicon carbide business. But until last year, we were called 26, and 26 probably rings a bell as a silicon carbide substrate supplier, both for power electronics and for RF, so semi-insulating and N-type for power electronics. Last year, 26 has acquired Coherent, and Coherent is big in laser business. And the decision was to rename the whole company to Coherent. Okay, so last year revenue was about $5 billion, nearly 30,000 employees. We have 4,500 engineers, 3,000 patents. And the magic word vertical integration also counts for us. I will tell more about this later. We have 3 business segments: materials, where we belong to, networking, and laser. So networking is telecommunications networking, transceiver, optical transceiver. Probably Ericsson is making use of that. And we focus on 4 markets: industrial, communications, electronics, and instrumentations. So I also will talk about automotive, and automotive kind of comes up under electronics here. Our total available market, which we address, is about $65 billion. So we have made our own calculations also about how to grow the company, and there was a period of significant acquisitions over time. So the company grew, let's say, over the last, grew from $500 million to around about $5 billion over time. So we acquired lasers, indium phosphide technology, epitaxial wafer and silicon carbide device technology, gallium arsenide technology, and optical networks as well. talking about the silicon carbide market. So these are numbers that are compiled from different reports, customer interviews, and our own estimation. So we believe that silicon carbide semiconductor demand is growing more rapidly than most of the analysts guesstimate. Nobody knows, but majority really will be driven by, I'm still mixed up with where to point, will be driven by the automotive industry. So about 40% will be contributed. So today we get requests for incredible high numbers in terms of demand for silicon carbide power wafers for the automotive industry. And then there is a portion industrial, renewable is still small compared to the rest, data centers and RF. So vertical integration, as I said, is a magic word, and there are reasons behind, because the demand today really is for substrates, silicon carbide substrates, and to get them you need to do your own crystal growth. So II-VI or Coherent is building the vertical integration up from the bottom. We have many years of experience in crystal growth and substrates. Acquisition of Ascadron here in the Electrum building in 2020 added epitaxy capability. We licensed the silicon carbide MOSFET technology from General Electric. And General Electric has done a very rugged design which works at high temperatures. So we make our own device fabrication, chips, and also then modules. So at each step, in terms of 6 substrates, epi, MOSFET, or module, we sell also to the external world. So we use our own substrates for, I apologize. We use our own substrates for making devices and modules, but at this stage also we sell substrates, we sell epitaxial wafers, we sell devices and modules to customers. So for substrate, II-VI, so Coherent, has been the first one worldwide to demonstrate an 8-inch silicon carbide power substrate. And this was already back in 2015. So why hasn't it productized faster? Because there was no demand for 8-inch at this time. This was the time where industry went from 4-inch to 6-inch, and the 8-inch step is coming now in the next years. So that's why it hasn't been productized faster. We are putting quite significant money into scaling the capacity. Just last year we have announced to invest $1 billion into this whole supply chain. And just in the last quarter financial results, our CEO said it's not enough. It's by far not enough. So more billions will be needed to cope with the demand which we currently see from the industry. For epitaxy, Ascadron is known for doing SiC epitaxy as well. So meaning we can provide epitaxial wafers for high voltage designs going up to 10 kilovolt devices or even higher. And also here we are investing a lot in capacity expansion. So we have 4-inch still, 6-inch capability, but also 8-inch capability is being installed as we speak. On the MOSFET design, sorry, again, I don't learn it. So as I said, we licensed from GE, MOSFET technologies that has been qualified for 200 degrees operation. So not only the chip, but also in the package. And the intention from GE initially has been going to avionics as well. So it is very rugged design. And even if you don't need this 200 degrees operating temperature, it allows you some room for, let's say, extended lifetime if you run it at lower temperatures, like at 150 or automotive sometimes wants 175 degrees. So there is headroom left, which you can use for performance, or it also gives you a longer lifetime. So in tests, we have measured that we can achieve up to 2.5 times longer lifetime with this device compared to competitive device. Likewise, on the module side, we have brought out a module 1.7 kilovolts, 600 amps, rated at 200 degrees, and it comes with ultra-low inductance for fast switching capability. Different locations. So 6 silicon carbide substrates are produced in Pine Brook. So there we have R&D, crystal growth, and slicing. In Eastern, we are just expanding this factory. We'll also do crystal growth. Epitaxy will be added, and it's about 30,000 square meter facility. In Starkville, we do back-end silicon carbide wafer processing, characterization, polishing, cleaning, and shipping. Likewise, in China, Fuzhou factory, characterization, polishing, cleaning, shipping, and it's also being expanded. In Warren, we do epitaxy, devices, and device test. Here in Kista, it's primarily epitaxy, but we also have R&D ongoing for silicon carbide devices. It's a small team here in the Electrum building, but highly skilled people that have been in the silicon carbide business since many, many years. And here is the foundation in Sweden. I mean, I'm based in Germany. But I was astonished about the wealth of silicon carbide expertise in Sweden. And this has started probably, I don't know, maybe 20 years back. So this expertise, unfortunately, has been acquired by external companies. But it's a real success story about silicon carbide with origins in Sweden. So there is another company which we acquired that do ion implementation. That also something you need in the semiconductor manufacturing process. So that's a picture of the Eastern facility. So they're doing 150 millimeter and 200 millimeter substrates, and soon epitaxial wafers as well. So we expect to reach 1 million pieces substrate output, mixed 6-inch and 8-inch together by 2027. As I said before, we currently see this is by far not enough. So the gap is widening between demand and supply, and there will be undersupply for several years to come. That's what our analysis does. So this is a slide about this MOSFET device we have, 200 degrees. Still today, it is the only one in the world that passes qualification at this temperature. And it gives you, as I said, significant margin at lower temperature operation, improved short circuit capability, and also it has a zero threshold drift across a wide operating temperature. So that's the final slide. What we provide are substrates. We are actually the second largest supplier of substrates. We offer 8-inch substrates as well and epitaxial wafers. Our epi capability enables devices from 650 volt to 10 kilovolt. And we have a very rugged MOSFET design, which gives long lifetime. And it's automotive rated at 200 degrees C. And on top, there will be modules as well. And as I said before, this is not just for internal use. This is at each of those steps is offered to external customers likewise. Thank you.
Thank you very much. Do we have any questions? One.
Thank you very much. I'm personally very interested in the super high voltage silicon carbide stuff. We did 5 years ago 15 kilovolt bipolar devices based on the Ascatron epi. What do you think will be the market? When is the market open for the 10 kilovolt and above? What's your plans on that voltage range?
So we maintain our expertise to do SiC epitaxy. Honestly, I have to say there are very rare, very few requirements for those kind of voltages. So the sweet spot today is 1200 volt, going up to 3.3 kilovolt, and then R&D activities up to 10 kV, but very, very few. But still, we want to keep this know-how, how to do this, because it's not so easy to grow 100 micrometer of epitaxy or even more. I mean, we have grown up to, I think, 200 something micrometer. Then it has a bumpy surface, which you need to manage, but it's doable, right? So it's customer driven at the end of the day.
Thank you.
Maybe I can just ask.
Yeah, just a short.
In the presentation before, we saw target price for a 200 millimeter wafer would be $800. When do you think we'll be there?
The question was in one of the presentations earlier. We had a target price on $800. What is the expectation?
Will take several years. So definitely, I mean, this needs to be in quantities like you sell 6-inch wafers today, substrates today, right? So it's probably, I mean, before definitely 2030, but I cannot be more specific. We are making our own estimations, but that's not for the public.
In the future. Well, thank you very much. I think unfortunately, we have to go on in the program. And last, but not at all least, we have Ganesh Chandramukhi from Alstom. Please, take the floor.
Thank you. Thank you. This morning I left my house at 5 minutes past 7, took my bike to the station, took the 17 minutes past 7 train to Sundbyberg, got on the metro, changed to the 155 bus at Resne, and arrived here on time for this event, which I'm very glad for. This whole journey was essentially, I looked it up on my Google Maps, and it was and I sat on the train, which was and the metro and so forth. It all had power electronics in it. That's the one thing I thought of. The other thing I thought of is, of course, that this may not be the norm of travel, but it does involve a lot of modes of transportation, and that's something worth bearing in mind. My name is Ganesh Chandramukhi. I'm head of innovation for traction at Alstom in Sweden. Alstom is one of the biggest providers of mobility services, primarily rail-based transportation in the world. We're about 74,000 people worldwide, out of which 2,200 in the Nordics. And in the Nordics, we have, in Västerås, we have a global R&D center for traction, R&D and innovation. So, the demand for mobility is growing. As you've heard before, more people living in cities, and we also have come to the same conclusion, which is good. And certainly there's a greater demand for rail transport. And all of this in the climate change context. So at Alstom, we continually prioritize innovation in these areas. We talk about green mobility, leading societies to a low carbon future. We talk about making mobility simple to operate and ride. And we have what we call inclusive and healthy mobility. So these are our 3 priority areas. And we do have innovations that we can demonstrate in these areas that, in fact, are driven by power electronics. For instance, we have our latest generation of traction systems, which we, in fact, demonstrated a few years ago in the Stockholm metro with silicon carbide MOSFETs, and showed that we could reduce energy consumption, size, weight, noise, etc. We also have energy storage solutions for onboard battery or hydrogen fuel cells, where we can run trains on lines which are not electrified, eliminating the need for diesel electric or diesel powered systems. But now, even if we do have energy efficient trains, we also need to make sure that whatever energy that we actually break when we try to stop the train actually can get fed back into the grid. And that's not always possible with a DC supplied system, which is the case in Stockholm actually. So there we have solutions where you can have reversible substations where you can feed back the energy back into the grid. So we have innovations that are ready to use. And the question is, does it mean anything? And if so, what? Well, I would say that rail is what we would say is one of the most sustainable modes of transport. We have about 300 times less emissions compared to road transport in Sweden. And there's a capacity efficiency that is about 5 times compared to road transport. So even if we go all electric with cars, we'll still have the congestion problem to consider. Now, energy efficient rail, of course, is good, but it will only make a difference if we actually shift modes to increase the modal share of rail transport. That being said, considering my trip, we do recognize that all modes are needed at the same time. So we probably need to look at a bit of a bigger picture about what's happening with the whole system. And I would say that there are actually 2 aspects that are really impacting the whole electric energy system. And this is my somewhat non-scientific view of what is happening. So I would say that there are 2 main transformations driven by the climate change that we're seeing. So decarbonization of mobility and process industry that are impacting the power demand on the electric energy system. We have an increase of demand in both cases, but there is a variability when it comes to mobility, especially when you look at geography and time, which is probably going to play even more havoc with our energy supply systems. So there is that dynamic to consider when we talk about mobility and energy systems. Now, are we moving fast enough with the innovations now, with like power electronics, to actually address these problems. And my take is probably not. Many of you might agree with me. And I'd like to give a personal take, somewhat from observations and some personal reflections on what might be barriers to introducing innovations. One of the things is that we're talking about systems of systems of systems. So what is a system? And depending on where you are you on the device? Are you on the complete grid? Or there is a definition there that you need to consider. And either that leads to that we work in silos, or we're paralyzed by the enormity of the problem that we're facing. Another aspect is, of course, that we have policy, procurement, culture, and processes, especially, I would say, in the railway industry, that is prohibitive for innovation. Actually introducing innovation, not just demonstrating, but actually introducing it commercially. There is the trustworthiness and dependability aspect of it also. So, of course, before you introduce something new, you need to really be sure that it's safe, secure, and dependable. And here, I think, especially with electromobility, we do face a lack of sufficient test and validation capabilities and capacity. When it comes to industrialization, I think it's been mentioned before, I think the change, what we're seeing, is that the economies of scale are different. And so we need to maintain and manage a greater variability and still have a cost-effective approach. And not least, we talked about the CHIPS Act and so forth, and CHIPS joint undertaking. The funding landscape, and this is a direct quote from a report I read in the UK, from the UK, but I think it's equally valid here. The funding landscape is difficult to navigate and is not output driven. So, what can we do about that? I would say that there are 5 priorities for government, public, and private actors to consider. We need to use the capacity we already have efficiently. So that means creating incentives for efficient use of capacity in the intersecting systems of energy and mobility. We need to create incentives for innovations with impact and build both the pathways to industrialization and commercialization, but also combine this systems perspective with the possibility for individual entrepreneurship and initiative. We need to be open while ensuring trust. So coming back again to effective testing and validation is one way of gaining the trust. We need to collaborate off the beaten track. That means that no industry or sector alone has all the answers. And I think that just like we're gathering here and talking about power electronics, I'm quite certain that there are other groups convening in a similar way, wondering why we're not considered as important. So we need to see how can we contribute to the overall picture. And not least when it comes to talent and competence. And then last but not least, we need to fight this fragmented innovation funding. And I have a few examples of what one might consider, or ways of looking at it. When we look at mobility and the intersection with the energy infrastructure, I have made up 4 scenarios. So if we look at the mobility infrastructure on the one axis, you could have either a very fragmented, decoupled mobility system, or the ideal seamless, interconnected system. And similarly with the energy infrastructure, you could have a bottleneck, decoupled electric energy supply system, or a balanced and integrated one. Now, the ideal situation then would, of course, be the right upper corner, where we have what I would call a seamless electrified mobility. And, of course, to get there requires this innovation, but only if we look at it from a holistic perspective. Looking then at pathways to industrialization. I was in Newcastle a month ago and was shown around some of the Newcastle University facilities. And what's a bit interesting is that they do have what they call the driving the electric revolution centres, industrialization centres across the UK, at some of these key universities, and actually somewhat akin to what you talked about, the MyFab. But here on a different level of integration. The idea is that they can build electric machines and power electronic modules, etc., wire bonding, all those technologies they have there, with the purpose to not to do the actual production, but actually to try out industrialization and actually help companies get there. Whether that investment per se is the most efficient way of UK taxpayer money, I won't say, but I think at least it might serve as some inspiration for us. Now, we had a discussion. I was in a roundtable a month ago talking about where we need to invest and focus on in the electronics and semiconductor value chain. So this is not a crystal structure that I'm trying to document here in any way, and I'd probably get very bad marks if I'd done that on an exam, probably. Now, the idea was to try to show, because we were talking about, we have the different stages of the value chain, right, on the one axis there, all the way from materials to the end product. And we have the different types of device categories that we're looking at on the other. And then we have some kind of technology generations. And the question is here, and this is for the same topic that we've been discussing here, where do we, as a country, as individual companies, etc., where do we put our bets? And there is a trade-off here to be considered with the investment and what the returns are. And maybe there are some sweet spots here for Sweden, and we'll have to find them. But there's also quite a lot of diversity in the needs from the different actors in this area. We talked about collaboration. One of the things we've done, and being focusing on effective testing and validation, one of the things we've done at Alstom here in Sweden is that we're opening up our Power Lab investors for external partners to be able to test power electronic drivelines. And we've already had a few partners doing that, clients doing that, and we're looking forward to more types of collaboration here, because that's a kind of a capacity and capability that's not very, what do you say, available. And then we talked about education and collaboration from that perspective. So growing competence and talent, there are shared challenges. And one of the things we've just entered into is a program called Redeem. It's run by 3 universities here in Sweden. And just as an example for what you could do with lifelong learning and research level education, and in certain key areas that are affecting not least electrification, digitalization, and resource efficient production. I think this could serve as potential models for how we collaborate between industry and academic institutes. Now, one thing about the funding infrastructure. It's good that we're talking about missions and impact, but I think there are different kinds of missions and different kinds of impact. So we have where we look at the impact on the society, but we also have enabler missions on the other hand. And they probably need to coexist. And the impact type of missions are actually, there are also different levels there of integration, demonstration, verification, and all the way up to the super system impact. And we also need to consider if there are challenges that actually are the ones that are driving, not the technology, but the challenges that are driving the evolution. So as an example, if we just looked at mobility, one way of looking at it is we could have what I called a seamless electrified mobility, which is one mission, but you also have enablers that are necessary, not least the electric energy conversion and storage. This might be a way of framing what we want to do as a society. And of course, there will be other impact missions as well, but that might be one way of looking at it. And then looking at this challenges and the roadmap related to that, this is another example from the UK. The Advanced Propulsion Centre has roadmaps, they have industry challenges, and they have value chain mapping for the entire electromobility area. It covers electric machines, batteries, power electronics, etc. Could also serve as an inspiration. And one way of looking at these challenges is maybe we could break down the impacts that we want to achieve to the right challenges that we need. So, a call to action. As I said, use the capacity we have, create incentives for innovation, open while ensuring trust, collaborate, and fight fragmented funding. And I think waiting is not an option. So, thank you.
Thank you very much. Do we have any questions? I think that was a perfect end of this day with those 5 crucial points to work on with. So thank you very much.
Thank you.
And Bellman and Claes, we would like to thank you all for being here today, and we hope that you have had a very interesting day, interesting discussions. Perhaps you have met some new contacts, and thank you for being here. Do you want to comment something too?
No, I'm fine. Thank you for coming, and hope to see you again next year.
Yeah, I'll just comment a little bit on what we've heard today. We've heard exciting new funding opportunities. We've heard about the need for doing something in Sweden. So, at the risk of sounding like a teenager or a kid in the back seat, are we there yet? Can we do it? Like, why don't we just do it? Let's just do it. So, I would like to urge the industrial community to ask for help. I think then we can, as Adela said in the morning, we need the industrial input and what you need. Yeah, thank you for coming.
And the last final word, thank you to KTH for us being able to be here today. It's a perfect room. Thank you. Thank you all.